Hey everyone, good morning, at least to those of you on the East Coast of America. It is quite unusual for us to gather at this early hour. I'm unused to speaking publicly at this early hour, so I'll do my best. Of course, we're doing it at this time because of the guest that we're going to be speaking to in just a little while, Sir Roger Penrose, who is in Oxford. I think he's in Oxford, certainly is in the UK. And to accommodate the time there, we are starting on our end a little bit early relative to what we normally do. But I guess for some of you out there, this is a really good time, those who join us from the other side of the world. In fact, if you don't mind, those of you who are willing, just in the discussion, if you can just say where you are watching from. I always like to see the variety of different places that we're able to reach with these conversations. So I saw a few earlier from various parts in the world: India, Argentina, Germany, Spain, Miami. That's an exotic one. Wow, that's scrolling by too fast for me to read. But Chicago, Rhode Island, yeah, a bunch of India, Switzerland, Amsterdam, Pakistan, Melbourne. I guess I didn't really pronounce that correctly. Melbourne. They always get on my case in Australia when I pronounce that incorrectly. But anyway, thanks for joining us. And we're going to be speaking to Roger Penrose, I don't know, in about 20, 25 minutes or so. What I'll start with first is a little discussion of maybe a little preamble to what Roger and I will talk about, and maybe take a few of your questions before we get into the conversation. As you no doubt know, Roger Penrose is one of the great minds in mathematical physics or mathematics. He has made impact in both of those arenas, as well as a crossover between the two. I don't even think he remembers the fact, there's no reason why he should remember the fact that, I went to Oxford as a graduate student, and I went there because I wanted to study with Roger Penrose. And on the first day there, I showed up in his office and we had a little chit chat kind of thing. And he told me what he was working on. And at that time, it was so, to my ears, so mathematical that it felt to me that it was too far away from physics for it to be something that I wanted to work on. And I was pretty upfront about that. And he suggested that I move over to talk about or work on, I should say, physics in the physics department, is right across the street from the Mathematical Sciences Institute at Oxford. So I was only his student for about 2 weeks. Then I moved over to be a student of particle physicist Graham Ross. I also spent a little time initially working with the astrophysicist James Binney. So it all worked out well for me. But the irony of it is, when I went over to work on physics, ostensibly, I got into string theory, as many of you no doubt know. And in that work on string theory, I had to make use of and learn and master and apply some of the very mathematical techniques that Roger Penrose was describing to me in our first meeting. So although I left working with him to do things that were less mathematical, I wound up doing things that were equally mathematical, just a couple hundred yards across the street as things turn out. But again, I don't even think he remembers that brief meeting, because that's all it really amounted to. But what we'll talk about with Roger, of course, is the work that resulted in his being anointed, if that's the right word here. He is a knight, so that's where the word anointed should be used. But the announcement from the Nobel Prize committee that Roger won the 2020 Nobel Prize in Physics. He shared it. And you may recall that we had a conversation with Andre Ghez, one of the two individuals that he shared the prize with, which is fantastic. That work, of course, is in the arena of black holes. It's the mathematical side of black holes. So we'll get into that conversation. But the other thing to really bear in mind is Roger is a thinker whose ideas span a whole range of different subjects. He's not one of those scientists who just drills down further and further in one particular area. As some of you, I'm sure, know, he has ideas about cosmology. We'll get into those a little bit. He has ideas about the arrow of time. He has ideas about mind and the relationship between mind and computers. Can the mind really be thought of as a biological computer? Many people use that analogy. Some people take that analogy really quite seriously. Roger has arguments based on Gödel's incompleteness ideas, incompleteness theorem, where he tries to argue, and to many people he has successfully argued, I'm on the fence on this, maybe he'll convince me today if we get into it, that the mind really cannot be likened to a standard computer, because he believes that the mind is able to access certain kinds of understanding that stands outside of the algorithmic step-by-step methodology that's intrinsic to computation, as we usually talk about it. So for him, the mind is something that certainly transcends that metaphor. It really cannot be likened to a computer. And he has ideas about where consciousness arises, and it has to do with some issues in quantum mechanics that we will also hopefully have a little bit of time to talk about. Issues in quantum mechanics that we have discussed in these sessions from time to time, the gap in our understanding of quantum mechanics. Not everybody believes that there is a gap. I am one of those physicists who certainly does believe that there is a significant gap, this quantum measurement problem, this, if you will, second step that has to be employed when using the framework of quantum physics. In quantum physics, we use the basic equation that Schrodinger gave us some time ago, but you take that equation and that's not enough. You then have to take that equation. I don't know if you're seeing that equation, but I see the equation right now. But you take that equation and then you have to augment it with a second step in which you go from the fuzzy nebulous probabilistic description that this Schrodinger equation provides you, and you have to extract a single definite reality from that haze of possibilities for which you have probabilities. How do you do that? And this is a question that many people have worked on. There are solutions that people have proposed. I would say it's fair to describe the situation as still unsettled. And Roger Penrose has taken that unsettled quality of quantum mechanics, and within there, he argues we may find the answers that we've been searching for consciousness. I'm skeptical. I have to say I'm highly skeptical. Many others are too, but it just gives you the sense of the boldness of thinking that Penrose has brought to bear on things that spark his imagination, which is a rare and wonderful quality. And so we'll get into that as we head onward. Let me just spend a couple minutes just giving a little bit of background on some of the ideas of black holes, so that this conversation just has a little bit of framing, because we may not start from the beginning. I'm not sure where we're going to go in the conversation. But many of you know, back in November of 1915, Albert Einstein was putting the finishing touches on his general theory of relativity. And he wrote down the final equations of the general theory in a paper that got published in 1916, but it was at the Prussian Academy in November of 1915 that he wrote down the equations. And this was a monumental moment in the history of scientific ideas. Gravity, the most pervasive and obvious force in the cosmos, was brought within a strong mathematical description, one that went beyond Newton's description, which had various puzzles and problems having to do with the speed with which gravity would be communicated from place to place. And so Einstein writes up this paper, and just about a year later, a German mathematician, physicist named Karl Schwarzschild, it turned out he was at the Russian front during World War I. It's kind of an amazing story. He somehow gets a hold of this paper and starts to calculate with it, and he comes up with a solution. The first exact solution to Einstein's equations. Again, I'm not exactly sure what you guys see, but I see that equation in front of me right now, popped up on the screen, which is wonderful. That's the so-called Schwarzschild Metric. And that equation describes the gravitational field around a spherical object. And in that equation, it becomes clear, if you just squint at it, that something unusual happens when the size of the object, the spherical object, gets sufficiently small. In fact, you can see it in the equation when R equals 2gm, Newton's constant, the mass of the object, multiplied by 2. When its size becomes equal to that number, which is known as the Schwarzschild radius, something strange happens. You get a 0 in one term. On the second term, you get something that looks infinite. So something strange is happening. And indeed, the interpretation of that is that you're getting what's known as an event horizon. You're getting a point of no return. If you cross that distance, if the object is sufficiently small, if it's within its own Schwarzschild radius, which is just a number, take its mass, multiply by 2, multiply by g. If the radius of the spherical object is small enough, if you crush it down small enough, then the warp in space is so significant that you can't get away. And by you, I mean anything. And as we love to emphasize, that also includes light. And if light can't escape from an object, then that object is black. And ultimately, this is what's known as a black hole. So, it's also interesting to note, I don't think we'll get into it with Roger, but you should sort of bear in mind as well, this possibility of black holes, not using that language, but dark or frozen stars, it actually emerged long before Einstein's general theory of relativity. Just to give you the full intellectual landscape here, the history of these ideas, way back in the 1700s, there was an English physicist. I think his last name is Mitchell. I think it's John Mitchell. I hope I'm not saying that. You can correct me if I'm wrong. Someone can look it up in Wikipedia right now. I think it was John Mitchell. He asked a very simple question, which is, okay, on the surface of the Earth, there's a certain escape velocity. I don't know what it is, 11 kilometers per second or something, but whatever. There's an escape velocity where if you throw an object up faster than that speed, it will escape the gravitational pull of the Earth. But then he noted, hey, even in Newton's theory, if you made the mass of the Earth bigger, then the escape velocity would be higher, not be up, it would be a larger number. The bigger the Earth, the bigger the source of gravity, the faster the object has to leave the surface to be able to escape the gravitational pull and just go off into space. And he said, what if you keep on doing that? Make the mass of the object bigger and bigger and bigger, make the escape velocity larger and larger and larger. At some point, the escape velocity will exceed the speed of light. If the escape velocity exceeds the speed of light, then light can't escape. The object goes dark. So this idea of a dark object, because gravity is so powerful that light can't escape, really does not originate with the Schwarzschild solution, does not originate in Einstein's theory, but it's Einstein's theory that supplants Newton's description of gravity. So the fact that there are these dark objects, at least in principle, according to the mathematics in Einstein's theory, means that you got to kind of take them seriously. You got to really think about them. And Einstein, when he encountered this result, I don't know if it had anything to do with the fact that Schwarzschild had beaten him to the punch. Schwarzschild gets the first solution of Einstein's equation. Einstein took his own equations and he can only solve them approximately. So Schwarzschild gets his exact solution. When Einstein sees it, he is completely skeptical, not of the situation where the object is larger than its own Schwarzschild radius, a star, the Earth, whatever. But he's very skeptical that there would ever be an object that would be small enough, that its physical radius would be within its own Schwarzschild radius, Schwarzschild number. And so he's basically saying that these dark objects do not exist. They're in the mathematics, but they don't exist. And to make the rest of the beautiful long story short, we now, of course, believe that they do exist. And the Nobel Prize this year is for the theoretical ideas that Roger Penrose developed to substantially bolster the mathematical case for the existence of these objects, as well as the observational case that came from the observational teams that studied the black hole that we now call a black hole at the center of the Milky Way galaxy. It's interesting, as I said, that I pause for a moment, because I suspect that Roger Penrose might not describe his own work as establishing theoretically the existence of black holes per se. We'll get into it a little bit, but what he really showed, as we'll talk about in a few minutes, is that singularities, places where the mathematics in some sense of general relativity breaks down, places where you can't extend the trajectory of a light beam any further, in some sense, places where space unexpectedly comes to an end. It's really time coming to an end, to be a little bit more precise. That's what his mathematics and his singularity theorems establish. Now, of course, black holes are an example of that, where you have an event horizon, this edge surrounding this singularity. But his insights really have to do with the singularity, not so much with the existence of the horizon. So I wonder how there's a little bit of subtlety there. And we'll talk about how the community responded to the theorems that he proved in the 1960s, which showed that this kind of singular structure deep inside, for example, a black hole, was an inevitable consequence of certain conditions within the general theory of relativity. So it's a beautiful story. Again, goes all the way back to the 1700s. And I like to think that that story, in some sense, can be thought of as, it's a dominant, specific collection of ideas that we'll talk about, but it's also the case that, in a sense, what Roger has spent a lot of his life's work on is thinking about things that are impossible or thought to be impossible from one way or another. What do I mean by that? Well, we'll talk about how Roger studied, and no need to show any of these things to the audience. That we'll talk about when Roger joins in. But he constructed various shapes that are impossible to build in the real world, but on paper you can draw them in a way that is both convincing and perplexing. Shapes, as it turned out, that inspired Escher in some of his drawings. Roger has been focusing upon the problems within quantum mechanics. Again, issues that some people think are solved, some people think can't be solved. He's been talking about issues in cosmology. What happened at the Big Bang? Was it really the beginning of it all? So these are the most perplexing questions, the kinds of questions that some people say are insoluble, impossible to solve. But Roger's all about trying to find the unexpected solution, the creative solution to things that otherwise people would suspect would remain puzzling forever. All right, let me take a question or two before we bring Roger into the conversation, just so that we keep this a little bit interactive. Escape velocity, someone confirms 11.19 kilometers per second. So I was pretty close. And I don't know if anyone confirmed the first name of Mitchell. I think it's John, as I said, but who knows? Sam Banner, one question I'll get to before we bring Roger in. When a particle of a particle-antiparticle pair that's entangled, when it falls into a black hole, what happens there? That's a good question. I wish we had 3 hours with Roger. I don't know how much time he's willing to give us. I think we probably have to wrap it up in about an hour or so. But That's a deep question, Sam, and it's really at the forefront of research today. Last few years, people have been deeply perplexed and coming up with all sorts of creative ideas for what entanglement between particles means when one has fallen over the edge of a black hole. Does the edge of a black hole in some sense snap the entangled quality of those particles? According to Einstein's ideas, that would not happen because, as we'll talk about with Roger, the edge of a black hole is not some special location in space from the standpoint of physically measurable qualities at that location. There's no signpost, there's no obvious marker that lets you know that you're at the horizon of a black hole. So classical ideas would suggest that that's not the case. The entanglement should persist right across the horizon. However, when you think about that deeply, together with what's known as the information paradox with black holes, as we'll talk about, Stephen Hawking shows 1974 that black holes can radiate. If things can get out of a black hole, the question is, do they show an imprint of the things that fell into a black hole? And in order for information not to be lost, they had better show an imprint, but that imprint, through a circuitous chain of reasoning that I won't try to recount right now, suggests strongly that the entanglement across the horizon of a black hole needs to be rethought. There's tension between the information being imprinted on the outgoing radiation from the Hawking process with the persistence of entanglement across the horizon. Those ideas are in tension due to something called the monogamy of entanglement. Yeah, physicists do come up with strange names of things, but it turns out that you can't have entangled particles that are in mutually entangled pairs, at least if it's maximally entangled. This can't be maximally entangled with this, and that particle be maximally entangled with something else further out. But that latter entanglement had better be there if information is to be imprinted on the outgoing radiation. Okay, there's the argument. I said I wouldn't recount it, but I just did. So something's got to give because everything can't be entangled in that manner. And some have suggested that maybe the entanglement across the horizon of a black hole gets snapped. And if it snaps, that can yield energy. And if you then look at the entire event horizon of a black hole, if you have these snapping processes all over that surface will have a lot of energy. Now it's a real thing. In fact, people have given it the name firewall, a hot surface that would incinerate anything that approaches it. So the whole idea of falling into a black hole is a subtle one when these quantum ideas come into the story. So yeah, Sam, that's a great question, one that as yet does not have a full answer, but I should say, maybe we'll talk about this in a subsequent discussion. There's been a lot of progress of late. I'm talking even in the last few weeks, few months, in making mathematical sense of these ideas. And I would say that there's growing consensus that the puzzles that people encountered in the one that I just described are nearing their conclusion, that people are getting more and more comfortable that there are ways of thinking about these things which don't have any internal inconsistencies and allow for information to not be lost as it falls across a black hole. I don't believe Roger agrees with that statement. Maybe we'll have a moment or two to talk about that as well. In one of the approaches that he has been developing, he makes use of the possibility that information is lost inside of a black hole. Many of us from the string theory community and the gravitational community that is informed by some of the ideas of string theory do not think that's the case, that we believe that information is preserved. But again, not a done deal, and it will be interesting to hear Roger's views. Now, the other thing I should say, Roger's not a great fan of string theory, as many of you know. In fact, he wrote a book, and I don't remember the exact title, of the book, but I do know that one of the words in the title was fantasy, and I think fantasy was his description of string theory. So maybe we'll get into that a little bit. Again, I'm not defensive about these kinds of things, as you all know. I just find it deeply interesting to hear a variety of different perspectives. All right, so I think Roger's going to join us in just a few minutes, assuming that time in the UK is still in sync with our time here. And if you have questions, feel free to jot them in the chat. I'll try to look. Sometimes it's hard during a live conversation for me to switch my attention over to grab questions. I do have someone who's going to try to pull out some questions on a separate sheet. So I just see a few of you have already asked some relevant questions, but yeah, like Darshana, doesn't Penrose often criticize string theory? Darshana Bulkar. Yeah, and we'll see what Roger's feeling on those ideas is today, and I doubt his perspective has changed on it, but it's interesting to hear in more detail what it is about string theory that strikes him as wrong-headed or going in the wrong direction, or perhaps even the word fantasy. So we'll see how that looks going forward. Terrence Lau, do you think there's matter that exists inside of a black hole? That's a good question too, Terrence. The inside of a black hole is a curious place. As I was mentioning, there are some who suggest that there might not even be an interior to a black hole. That's one idea that people have floated. But in the more traditional approach, matter crosses over the edge of the horizon of a black hole. The matter doesn't disappear. It just is in a different location. And so as that matter is pulled closer and closer toward the center, the singularity of the black hole, it still exists, of course. It's within the event horizon of the black hole. The deep question is, what happens when it hits the singularity? Does it still exist? Is it somehow flushed out of our universe? Is it thrust into a different universe? We can't really answer these questions because of this singularity, the singularity that Roger Penrose proved is there. And the curious thing we'll talk about with Roger as well is that, singularities, it's hard to really understand what they mean, because they are in essence a diagnostic tool that shows us that our mathematics breaks down. If our mathematics is breaking down, it's breaking down. So it's not as though the singularity is a thing. It's not like a marble. It's not like a diamond or a jewel. It is a diagnostic, which basically is nature, or the mathematical description of nature, telling us that things are not working. All right, so let me now, with that preamble, give a brief introduction to Sir Roger Penrose. Roger Penrose is the Emeritus Roosevelt Professor of Mathematics at the University of Oxford, Emeritus Fellow of Wadham College at Oxford. As you know, and as we discussed, he was recently announced to be a recipient of the 2020 Nobel Prize in Physics. He's previously won a great many awards, so many that it would take half our session to describe them. Many of you know Roger from his wonderful books for general audiences. Emperor's New Mind was the first book, wonderful book that I remember reading in the 1980s. Very impactful book for me. The Road to Reality, this deep and expansive tome on the mathematical approach to describing the world, back in 2004. And his work on black hole singularities in the 1960s is what we'll talk about here today, as that's what he has been awarded the Nobel Prize for. So with that, let me bring Roger Penrose into the conversation. Hi, Roger, how are you?
Hello, I'm fine, thanks.
It's very good to see you. I was just trying to think the last time that we crossed paths. I think it was at a discussion of cosmology at Princeton. Do you remember that? It was
I definitely remember that occasion, yes.
Yes, right. I think it was maybe 2015, 2016. I mentioned to the audience, you probably do not, right? I would be shocked if you did remember. Do you know that I was your student at Oxford for about 2 days? Do you remember that?
I knew I knew you were, yes. I don't know whether I remember you specifically then, but
Yeah, we only met once.
Yeah,
Yeah, we met once, and you described to me some of the
yes,
work you were doing.
yes, I know.
Yeah, and it was on the sort of more mathematical. I was describing to the audience how it's somewhat ironic that I switched over to physics because I wanted to do less mathematical things, and then I wound up doing string theory and algebraic geometry and compactifications just a couple hundred yards across the road over at the physics building. So go figure. That's how the world works. In any event, deep congratulations on winning the Nobel Prize.
Well, thank you very much.
Yeah, it's must have been a thrilling moment to be recognized in that way. And I'd like to talk about some of the work on singularities, black holes. Perhaps we can even get into some of your other ideas in cosmology, maybe a little bit on quantum mechanics and consciousness if time permits. But can we start, as it's always nice for our audience to just hear a little bit about your own background, if you don't mind. I was reading an interview, and it was interesting to me to hear you note, and again, perhaps the interviewer got it wrong, so correct me if I'm wrong, that when you were young, you were really good at mathematics, but you weren't the fastest kid. You needed to be given extra time to actually do as well as you could. Is that accurate?
I was always very slow. Yes. No, I mean, I could do it, but I was slow. No, this was actually in Canada during the war years, and I think I was I forget exactly which grade it was, but I hadn't done particularly well in maths, and I had a teacher who I regarded as very insightful. He was Mr. Stinnett, and he realized I got fairly low marks, but I think he realized also that I got low marks because I only got about halfway through the paper. So he decided that he would let me have the end of the period, which after that there was a play period, I think. And he said, well, look, you can keep on going right the way through the next period. And occasionally I needed even a bit of the next period after that. But then I used to do pretty well. I used to get in the 90s, and he recognized that I was just slow, not stupid. Although I did get moved down a class. Yes, in my first year when I was in Canada, I was in a combination of high grade 2 and low grade 3. I was in low grade 3. And my teacher there decided I was too stupid being in low grade 3, and she moved me down into high grade 2. But then she couldn't quite fit me in the crack between those two. So eventually she moved me up into high grade 3, which was better. It's better because I couldn't stand her. Sure, she couldn't stand me, I think was the main thing. I don't know what it was. I was just too slow.
That's so interesting. It's funny because when I give final exams in my classes at Columbia, I don't make them timed. I tell the kids, you come in and we set it up in such a way that they can sit, and some have stayed as long as 12 or 14 hours. We'll start at 3 o'clock in the afternoon, and I have a TA, and sometimes someone leaves at 5 or 6 in the morning, because my view is very similar. I don't care how long it takes. I just want to see whether you can get it done.
No, I think that was certainly right. I mean, I did speed up a bit afterwards, and I managed to finish papers. But
and so when you were young, were you doing mathematical problems? Were you tinkering with puzzles, and was that the kind of kid that you were?
My father was, well, he was a scientist, but he worked in human genetics. But he was really interested in mathematics. Also, I had an older brother who was he was different from me. He was very precocious and went way ahead. But he also was interested in mathematics and physics. I learned a lot of physics from him. But for my father, a lot of mathematics. And we used to make polyhedra and various things like that. And we had a great interest in that. I remember one occasion when I noticed there was a pattern on one of the floor. I think whether it was a floor or a sink surface, I can't remember. But it was a tessellation of regular hexagons all over, you see.
Yeah.
I looked at this pattern and I asked my father, well, look, suppose this thing extended way, way over around, and could it go all the way around the Earth and make a sphere, you see? So he said, no, you couldn't do that. but you could do it with pentagons. So he taught me about a dodecahedron, you see. So,
Wow.
so it was of course, that came back again with the non-periodic.
Yeah, so that was at the origin of your thinking about the what's now known as Penrose tiles?
I think more the origin was something else that I got from my father, which was actually, he had a book due to the famous physicist, mathematician, Kepler, Johannes Kepler. And in this book, there was a picture with all sorts of non-crystallographic designs. I mean, they were, see how far you can get with octagons and things like that, and mixed up with hexagons and things like that, little patterns with combinations of these. And the biggest one had a lot of pentagons. And I had seen that before, although I wasn't thinking about it when I was finding out about these non-periodic pentagonal patterns. But then later on, well, there were two amazing things about that picture. One of them was that I think it was shortly after quasicrystals, and people were seeing the 5-fold, 10-fold, and the 8-folds. And I went to Switzerland and visited there, and I was talking to a chap called Nissen, and he had claimed that there were 12-fold ones. Nobody had believed him at the time. And then he showed me the diffraction patterns. And I looked at the diffraction patterns with the 12-fold, a little dodecagon, and then little squares and pentagons and things all the way around. And I thought, I sort of arranged the dots. You see the little, you get bright spots on the Bragg peaks in the diffraction pattern. And I noticed they made little shapes like pentagons and squares and things. And I joined hexagons and squares and things. I joined them up, and I made this pattern around the, and slightly going inwards from the dodecagon. And I looked at this thing and I said, I'm sure I've seen that picture before. Where have I seen that? And I realized it was in the Kepler picture, and it was one called FF, I think it is, just right over at the side, and it was exactly the same pattern. Wow. But the other thing was, the biggest one with the pentagons, later on, I think I was giving a talk, again, bringing in the Kepler, and I wondered whether this pattern of pentagons would fit into my own patterns. And I found a place where exactly the same lines, including some little lines he put in inside one of the he had decagons, decagons and pentagons, things like that. You couldn't quite tell where it was all going, but I took this and I managed to match it with one of exactly in the middle of one of my pentagon patterns. Huh. So he more or less had it before.
Wow.
Much closer than the Islamic people. And people often said maybe in Islamic tilings you might see these things, but they have interesting patterns with pentagons and things, but never one of these things. But Kepler did. Remarkable, very remarkable.
Yeah. Now there's also, I was reading that you were inspired by a impromptu trip to the Van Gogh Museum.
Oh gosh, yes. Yeah, that was fascinating.
What was that about? That was an Escher exhibit, is that right?
That was at the, there was an International Congress of Mathematicians. They have those every 4 years.
Sure.
And I think I was in my second year as a graduate student in Cambridge. And somebody told me, I guess I learned about the International Congress, which was in Amsterdam in the Netherlands. And so I went to it with a friend. And then I remember seeing one of my lecturers there. This was Sean Wiley, who taught me about algebraic topology. And he had in his hand a catalogue. And it had this Escher picture with the night and day, with the birds in the night going one way and the white birds in the dark and the dark birds in the white, and then sort of meshed together in the middle. And I thought that was extraordinary. And he said, well, you go to in the Van Gogh Museum, there is an exhibition by this artist, M.C. Escher. I'd never heard of it before, or him before. So I went there and I was absolutely stunned by the amazing things there. Particularly the one called Relativity, with people going upstairs. And do you know the picture with a...
I think I do know that one. Now, didn't you and your dad start to draw?
Well, it was, I came away from that exhibition. I think it was in the vacation period afterwards. And I thought I would like to draw something that I hadn't quite seen in the exhibition. And I put a picture with roads and bridges and rivers going off in possible ways. And I whittled it down, simplified it to this thing people now call the tribar.
This is the impossible triangle thing, is that right?
And I showed my father, and he showed it to all his friends. It made them feel a little ill. My father decided to draw buildings. Yeah, that's it. Yes, he drew buildings, impossible buildings, and then he came up with the staircase. And so we decided we'd write. That's it. We'd write a paper about this, which we did, but we couldn't decide which journal to send it to because we didn't know what the subject was. We had no idea what the subject was. So my father said, well, I happen to know the editor of the British Journal of Psychology. So perhaps we'll say psychology and send it to them.
Right.
So
this is a staircase in which you continue to walk upstairs, and yet you still find yourself at your starting point as you go around.
Yes. So anyway, we published this, and then we credited Escher in the acknowledgements and sent a copy to Escher. I mean, for Escher's the museum.
Yeah.
I think the catalog in the museum. And in the meantime, Escher had produced Belvedere, which was a picture with a similar kind of impossibility.
Is that the one with the waterfall?
No, he did the Belvedere is a sort of building with it's got pillars which are joined up in an impossible way.
Got it. Okay.
And then my father sent a copy of this paper to Escher, and he got a copy, and he then had a correspondence with my father quite a bit. And the staircase was the first one he did based on this is called ascending and descending.
Right.
The waterfall he did a little bit later.
Got it. That's amazing. So let's turn then to the initial work that you began to do thinking about relativity and ultimately what turns into black holes. So, between 1915, when Einstein wrote down the equations, and say, mid 1950s and so forth, general relativity was no longer the exciting arena of physics. Most people were focusing on quantum mechanics and nuclear physics, atomic physics, things of that sort. So when you started to think about Einstein's ideas, were you kind of off in a quiet area of research at that point?
I wouldn't say quite that. There was quite a bit of activity, but in Britain, it was almost entirely in mathematics departments, I think, entirely, as far as I know. People were, playing around solving the equations in clever ways, and that's what they were doing. I got interested, I guess, let's see, it was in 1958 when I was back in Cambridge as a research fellow. I was doing pure mathematics when I was a graduate student, algebraic geometry and things like that, but I learned a lot about tensors and how useful it was to draw little pictures with arms and legs which joined up together rather than indices.
Huh.
And
I don't know if I've ever seen those pictures.
You haven't seen them?
I don't know if I have.
Not sure I can illustrate. Oh, I guess I could.
It looks like you have a whiteboard behind you there, but I don't know if it'll show up on the camera.
Yes, I could use that, but
I guess I can imagine you're basically tying together the indices from different tensors as opposed to just having repeated letters.
Right. And they just join them with lines. That's right.
Yeah.
There is a picture in Carlo Rovelli's book. I just see if you can find that. I've got it here. I'd have to find the right page.
Yeah. Okay.
Enough. But anyway, yeah, you just, instead of seeing an index here and an index here, just draw a line.
Draw lines. Yeah, sure.
And then I developed various notations for symmetrizations, and then you can do symmetrizations on top of anti-symmetrizations. And this is very useful in many areas of physics and mathematics. And but I had a good friend, Dennis Sharma, who I got to know primarily because he was a friend of my brother's, Oliver. Oliver was at Cambridge doing physics, and I was doing an undergraduate degree in London, University College London, in mathematics, which included applied maths, which was a lot of physics in that. But I remember being inspired by radio talks by Fred Hoyle. And Fred Hoyle was, I think there were about 5 of them. He started with the Earth, and then he moved out in cosmology, and eventually talked about the steady state model, which he and Bondi and Gold had developed. because there was a paradox in those days about cosmology, because people had worked out the age of the universe, and they'd also worked out the age of certain clusters of stars called globular clusters. And the globular clusters were older than the universe,
Right.
which seemed like a paradox. And so the steady state model emerged out of that. So, well, the Big Bang was not really the beginning at all, and you had a steady state model. It was actually due to a mistake, because the astronomers had mixed up two types of variable stars, Cepheid variables, and, and they got the wrong ones, and therefore they got the universe too young. But that wasn't known at the time.
Right.
And Hoyle was describing this in his radio talks. And he said, when the galaxies recede from us, and they recede, you see, you need them to recede, and then in the gaps between the galaxies, you get new material, hydrogen produced.
Just popping up, I guess, in that approach, right?
Yes, that's right. It was a clever idea. I mean, it was wrong, but it was a clever idea. And I quite liked it. And I heard Fred Hoyle talking about the remote galaxies as they, well, you see, when they got faster than light, they would disappear. So he said they would just appear when they got faster than light. I thought this is a little strange. And I started drawing little pictures with light cones. And what I really saw what happened is that they didn't disappear. They just faded away gradually. They got dimmer and dimmer and dimmer.
Yeah.
And so I was visiting Cambridge, and I visited my brother in the Kingswood restaurant, and I was sitting down having lunch with him. And I explained my puzzle to him about the galaxies disappearing. And he said, well, look, I don't know about cosmology, but sitting on the table over there is a good friend of mine, Dennis Sharma, and he knows about cosmology, and he'll tell you the answer, you see. So I went and talked to Dennis, and I drew my little pictures with the light cones, and he hadn't seen this before. And he said, well, I don't know about that, but I'll talk to Fred and ask him. But apparently this made an impression on him. So that when I did go to Cambridge as a graduate student, Dennis was absolutely, he sort of got hold of me and said, look, you've got to learn about physics, and
I see.
an awful lot of physics and cosmology. And he used to drive me to visit Stratford for the plays, the Shakespeare plays and things like that. So we used to go quite commonly, and he would drive at great speed around these windy roads.
To test relativity, no doubt.
Exactly. It was this Marx's principle. He was a great fan of Marx's principle. So he said that
so you were the rotating bucket.
Well, it was he was going to go around the road with great speed, and throwing him to the side of the car and said, no, that's the action of the fixed stars. You see. that was his.
So without the stars, you wouldn't have felt that centrifugal force just now as we whipped around.
That's right. So we thought, look, suppose you remove the stars one by one, what would it be like? What would happen to the inertia? Would it be determined by the car? Then you take the car to pieces. What's left, you see? No, that was quite an important influence on me. Indeed, yeah.
Just I don't want to go a diversion too much, but do you agree with that perspective? Do you think that without the distant stars, if you were to rotate, you wouldn't feel?
I'm not sure about that. Well, it doesn't. Einstein never. I mean, it was a big influence in his origin of the theory, but it never really worked.
Right.
It did fit in with his model. No, I'm not really a proponent of that scheme, but it did lead to this scheme of spin networks.
Yeah.
Which was, you just whittle it down to a few spinning particles, and how do they know how they're spinning and so on. But yeah, so it influenced me in that direction.
So what then pushed you in the direction of thinking about what we now, they weren't called black holes?
Well, it was 1958. I'm getting there.
Okay, yeah.
This was when I was back as a research fellow, and Dennis said, I'd already got interested in relativity at that time. Because Dennis was, I think. And then he said, well, look, come with me to a lecture given by this fellow, David Finkelstein, at King's College London. And so I went, and David was explaining how, with the famous solution called the Schwarzschild solution, which describes a spherical body in Einstein's theory.
Yep.
And we usually just think about the vacuum outside the body, because Schwarzschild also had a way of describing the matter inside, but that wasn't so important. It's really the outside. But then you imagine squashing this body down and down and down until it reaches this scale, which is called the Schwarzschild radius. And at the Schwarzschild radius, if you look at the formula, the equations, you see it just goes crazy at that point. And it looks as though you've got a singularity. That is to say, it looks as though things go to infinity and zero, and it just doesn't make any sense.
Yeah, I think we have that equation. We can probably bring it up as you're talking. Yeah.
At this r equals 2m in appropriate units, when the radius reaches what's called 2m in appropriate units, and for the sun, I forget, it's just a few kilometers.
Yeah, 3 kilometers for the sun.
3 kilometers or something, yes. For the Earth, it's, I don't know, about that big or something.
A couple centimeters, yeah.
Yes, and but people thought in those days, well, you never would squash anything down that far. So what's the problem? But Finkelstein's talk was a more theoretical one, and he was describing how if you change the coordinates to sort of infalling ones, and then the light cones are tipping over like this, then you get rid of that singularity. And I was very impressed by this. At the end of it, he talked to me, and I told him about spin networks, and he told me about relativity, and we sort of swapped subjects. Considered, because I was working on combinatorial physics, and then I changed to general relativity, and he changed from general relativity to combinatorial physics.
Quite an impact you both had on each other.
But anyway, I thought when I came back from the lecture, I thought, well, gosh, he's got rid of that singularity r equals 2m, but there's still the one in the middle. Maybe there's a theorem of some sort which shows you can't get rid of this. You push them this way and that way, but you just can't get rid of it. I thought, well, what do I know about general relativity? I mean, I've never seen anything like that. What do I know about general relativity that other people don't know and maybe might have missed, just sort of some way of looking at it? Well, what do I know? Well, I know about two-component spinors. And why did I know about them? Because I was playing with general sort of tensor systems, and usually in an algebraic way and with these diagrams and all that stuff. And I couldn't see how the spinors fit into this. And so Dennis gave me an incomprehensible book by Corson, a very good book, much of information in it, but it was very incomprehensible. But then, curiously enough, very strangely, I think at that stage when I was in first year as a fellow, I went through the second part of the course of quantum mechanics given by Paul Dirac. I'd been to the first part of the course when I think it was an undergraduate. Then I went to the second part of the course. And curiously, in the middle of this course, he deviated from his standard exposition and talked about two-component spinors. Now, I just thought this is great fortune. But I learned afterwards, talking to people who went into Dirac, I think there was a biographer or something who I was talking to, a woman who was working on his early papers. And she said it was most unusual for Dirac. I think it was she, or maybe it was Graham Farmer, who told me it's most unusual for Dirac to deviate from his course. So I don't know, but it happens that Dennis Sharma was his only graduate student around about that time. And I think he possibly mentioned that if he talked about two spinors, there's somebody who might be interested in him. But he did. He gave a very, very clear 2 or 3 lectures on it.
Yeah.
Made absolutely clear to me. And so that was the thing I knew. And I knew that you basically split your tensor index into 2, and one's a spinor, and that's the complex conjugate of it. And that's a very beautiful idea. But then I thought, well, let's try and apply this idea to general relativity. I haven't seen anybody do this before. And it works amazingly well. I was quite surprised how well it worked. And the main point was you got a very good understanding of the Vial tensor. You see, the curvature tensor, they're called the Riemann tensor, and it splits into 2 pieces. Yep. And one of these pieces is called Vial, W-E-Y-L, Vial tensor. And the Ricci tensor is the other part. And that part describes directly the matter.
Yep.
So it's like the charge in electromagnetism. In electromagnetism, Maxwell's equations, you have the charge current vector, which is the source. Then you have the Maxwell field, which is the field. So the Maxwell field is the photons, if you like. Now we quantize things. It's the electromagnetic field. That's how we can see each other. Without Maxwell, we wouldn't be here. We wouldn't be seeing each other.
Or we wouldn't understand why we're seeing each other.
Well, people wouldn't know how to do it, I guess.
That's true too.
I mean, I think it's important. Huge revolution in physics that quite unrecognized to the degree it is by the general public, I think.
Yeah.
a huge revolution. But anyway, that's not the thing I'm mentioning here. But in the Einstein theory, you could do a similar thing. You have the Ricci tensor, which is the source, and then you have the Vial tensor, which is like the Maxwell field. And when you write it in spinors, the equations look just about the same. It's got two more indices, but it's just 4 instead of 2. And it's very similar equation. So I really understood about how the curvature acted on light rays because of the spinors. And that was very useful to me.
Right.
All this is sort of background. And this is much earlier. This is 58.
Right. But can I ask you one question on that before we get into the details of what it is that you use this technology to prove? You said that you're at Finkelstein's talk and he shows that the singularity at the horizon at r equals 2gm over c squared, that is just a coordinate singularity. That's not a real singularity. By changing your description, you can show that the math doesn't blow up, no problems there. And then you said, but there's still this other singularity at r equal to 0 at the center of this solution that Schwarzschild gave us. And you said that your motivation was to figure out some way of proving that singularity could not be gotten rid of. But most of us sort of approach things the other way, right? It's like we want to get rid of singularities, right?
Well, it's not a question of what you want. It's a question of what's true.
But what was motivating you to think that you couldn't get rid of that singularity?
I don't know. I mean, it's the thing is the curvature there is infinite. That's
yeah. It goes like 1 over r to the 6th, I guess, as r goes to 0, right?
It blows up like crazy as you get to the middle. But of course, that doesn't tell you that if you had an irregular case, that was what I was thinking about. Suppose you perturb it, does that singularity remain?
So physically, that would be rather than just spherical stuff falling in perfectly spherical all the way, it might have a shape that's not symmetric, and then maybe it wouldn't all collapse right at the center, so you wouldn't have a singularity.
That's right. Well, you see, as I learned later, but I didn't do much after the Finkelstein talk except familiarize myself about spinors and how light rays behaved in accordance with the Vial and Ricci tensor. You could see clearly the difference between the two. The Ricci just focuses. It's like a positive lens, and the Vial is like an astigmatic lens. So it squashes and stretches like that. And so I appreciated all that stuff. But it wasn't till much later, I guess, in the 60s now, when I was at Princeton. Well, I'd been at Princeton and I got to work on gravitational waves. John Wheeler, who was very interested in GR, and I think quantizing was one of the things they were trying to do there. I didn't much care for the way they were doing it. Then I went it was a 2-year NATO fellowship. And for the it was about a third of the second year, I went to Syracuse University in New York State, where there were an awful lot of relativists there, including, Peter Bergman, who had been Einstein's last
student. Yeah, right. Yeah.
And then there were people like Arthur Komar and, Engelbert Schucking was there, and various other, André Trautmann visited just after I went there, and Ted Newman was the big, Ivor Robinson, Ted Newman. Ray Sachs, I think, was in the army at that point, but he did visit. I remember talking to him. But Ted Newman I got to know very well, and we developed spinor sort of techniques for looking at GR. But the main thing was more later on, when I started thinking, I guess I was back in Princeton again later on. Just trying to think what the ordering of this. It was in London when I was back in London when the you see, the point was the quasars had become puzzling to people. These were these very bright radio sources, which seemed to be not only 100 times brighter than an entire galaxy, or whatever it was, and
very small too, I guess.
Very small, so smaller than the solar system, because they had variations which indicated, that the speed of light to get across from one side to the other, they'd have to be smaller than the solar system. And this was indicating to people that you are looking as though you were down to the scale of the Schwarzschild radius, the R equals 2m, or you get it with a with constants in. But just at that scale, you can see you're playing around with that scale. Let's just say these actually, you've got physical phenomena which are probing that kind of scale. So various people, including Fred Hoyle and his collaborators, were looking at the possibility of maybe gravitational collapse. I don't think they were thinking about black holes in the sense we do now, but they certainly thought that something funny was happening down at this Schwarzschild radius scale, which happened to be the case, but they didn't know really what was going on. But the whole question, you see, I guess this was in the 60s, in 1964. That's right. In 1964, I guess I'd been to some conferences or something about it, and John Wheeler had worried me. I can't remember whether it was, yes, I must have been at a conference then. And John Wheeler was worrying about whether these singularities were real or not.
Yeah.
And there had been this paper in 1939 by Oppenheimer and Snyder, where they studied a dust cloud. So this means it's matter with no pressure. And it's falling completely symmetrically in towards the center, spherically symmetrical to the center. And there you got this singularity in the middle, which is infinite density. And this is a picture of a black hole. That's the one people use often to describe a black hole. But people were suspicious of this for two reasons. One was it was dust and therefore no pressure. That actually, as it turns out, was not a good reason, because pressure works the other way. But that wasn't the point.
It makes gravity stronger, actually.
Yes, but then nevertheless, the fact that there's no pressure meant somehow there's nothing to stop the particles coming together. And the main point is it's just focusing right into the middle. So of course you get a singularity. There's nowhere else to go. I mean, just aims at the central point. Yeah. And this would seem to be an artifact. Give it a little bit of irregularity, it swished around and comes squarely out again. And this was given a lot of credence, particularly because there was a paper by Lifshitz and Kalatnikov, two Russians, where they appear to have proved that in the general situations, you did not get singularities.
Yeah.
These were only artifacts of special case singularities. And this paper was out in the journals, and I had a look at the paper. I certainly looked at it, but I didn't, there was a mistake in it, which was discovered, I think, by Belinsky later on, and he then joined with the other two, and they corrected it. But this is part of a result of the work that we've done to show that singularities are actually quite generic.
Now, Einstein himself also wrote some papers.
Oh, yes, yes. No, I don't think Einstein, you see, let me finish the story here because yes. Let me finish this story and I'll come back to what Einstein would have thought, because I think you're absolutely right. As some other people, he probably would have had a similar, let me come to that. So I was trying to think what happens in the general situation, and did I believe Lifshitz and Kalatnikov? I looked at the paper, not knowing the mistake in it, but I just had the view that I didn't quite see that you could properly prove anything using that method. I mean, maybe you could, but it wasn't sufficiently persuasive to me that they were right. And I thought quite likely it wasn't true that you did get singularities in a general situation. I remember walking in a park. I used to live next to a park, and walking in that and trying to imagine myself in this collapsing material. And I came to the view that it had to be that if it was a local problem, if curvatures getting big, they just would go out again. But if it was something non-local, some non-local condition all the way around in some sense, that it would have to be a condition of that sort. Now, I didn't know what to do, but I had, for another reason, there's a lot of coincidence in these things. I had been writing in 1964 another paper on something quite different. This had to do with the asymptotic properties of fields, including gravitational fields, as you go out to infinity and what happens at infinity. And I had this trick for conformally transforming infinity, squashing it down into a finite region.
Penrose diagrams that we now call.
It was a much easier way of thinking about what happens at infinity, as you don't think of as infinity, because I was no good at doing all these things with limits, and everybody was doing limits and orders of magnitude and so on. I didn't like that kind of stuff. So I thought geometry, squash it down, and you can see where infinity is. And it was, I could see it was a very useful way of thinking about it. But the main thing was, this is now not about infinity, but I was writing this paper, which was about the papers of infinity. And I got stuck at one point, because in order to prove that the gravitational field behaved in the right way, it's the sort of peeling properties that Ray Sachs had. Let's not go into that here. But there was a very beautiful way in which the curvature peeled off as you came in from infinity, really. And I had a nice way of looking at that. And it had to show that your Vial curvature, your conformal curvature, had to be finite at infinity. And I couldn't quite prove that unless infinity had to be spherical. That is to say, you look out at the sky and you see a sphere out there. And if you think of that's infinity, well, there's that sphere and then there's time. So the infinity is a three-dimensional space which consists of that celestial sphere in time. But it's really the one in the other way. You're looking out, your light is going out rather than coming in from, but it's the same picture. So it's the sky right out there. But I couldn't quite prove that it worked if the sky had a funny topology. It might be a torus, thing like a shape of a surface of a donut. Yep. But then the proof didn't work. So I thought, well, this is a nuisance. I thought any sensible person would say, well, just assume it's a sphere. Of course it is. I thought, well, look, maybe it's not. It would be, maybe you can prove it's not. It's actually a sphere. So I developed an argument looking at boundaries of futures. You take a point and you look at its future cone. So it spreads out. So there's this cone in space-time, the point makes this cone, but then it's going to cross itself, do all sorts of complicated things, but it still makes a sphere if you understand the way these crossings and how they behave and what the boundaries of futures look like. So I got a good feeling. I sketched out a proof in the appendix. It was a bit sketchy, but I think it's essentially okay. But the point was, I got familiarity with what boundaries of futures looked like.
Right.
And so then the next part of the story was when I was back in England and I was working at Birkbeck College, and a friend of mine, this is Ivor Robinson, who's an Englishman, and he was working he headed a department in relativity in Dallas, Texas, which wasn't part of the University of Texas at that time, but it was an institute. And I don't know what he was talking to me about, but he had a wonderful way of speaking, and the Americans all loved him because he did have a wonderful way with words, there's no question about it. And he was talking to me like this, and just all of a sudden he waved his arms around like this. I was walking down the street, going towards where my office was. Yeah. Walking down the pavement, the sidewalk. Sure. And then we got to a crossroad, and as we crossed the road, we had to look out for traffic, so the conversation stopped. And then we got to the other side and he started talking again like this. And so then when he left, I started thinking, I got this strange feeling of elation, that something had clicked just as I crossed the street. I didn't think it was crossing the street. I had to go through all the things in the day. What was it? Was it something I had for breakfast? Was it walk I'd done later, or what was it, this or that? No. Then it came back, oh, it's crossing the street. I know what it was. So I had this idea of what happens when you're just inside what we now call the horizon. The light rays, you imagine a two-dimensional surface. So it's just like a balloon. Yeah. And in this balloon, there's a flash of light on the surface of the balloon. And that flash of light, if you normally think if it's like an ordinary spherical light balloon with the one side concave and the other convex, yep. Then on the concave side, the light would converge. On the convex side, it would diverge. But if this balloon were just inside, surrounding the material and just inside what we call the horizon, the light rays on the outside would be coming in as well. And so they'd both be converging. And if they were both converging, you don't need it to be actually spherical. It can be an irregular balloon. But if light rays are converging on both sides, then from what I knew about the futures of boundaries, that you'd have a compact boundary. And I knew that you could prove something from that you'd have to have a singularity.
So that was the trap surface that you were able to.
So it was the trap surface, which was the key to characterization of a collapse which has gone too far.
Right.
And it's not a local characterization, because you can have trapped surfaces locally. You can just take two past light cones and they intersect, which is locally trapped. So there's nothing wrong with it being, but it's trapped locally, but all the way around. And that's the problem. And when you get that, you have a singularity. So the proof, as long as the energy density, that is to say the light rays, there's a general tendency for them to focus inwards if the Ricci tensor has a positive focusing property. That means positive energy. So if it's or non-negative,
right,
it doesn't have to be zero, is still all right. If it was negative, that would wreck the theorem.
So your Nobel Prize winning result, you actually came to by following this sense of elation.
Yes.
Reconstructing during the day when it happened.
Yes.
And extract. Have you had other moments of elation that?
I haven't had one that I'd forgotten. That's, I think, the only time I'd forgotten it. No, I have had ideas which I've forgotten and resurrected. That's true.
Right.
Yeah. Yeah.
That's an amazing story. That's an amazing story.
Quite like that one.
So you write this paper where you write up what you just described to us so beautifully. What was the reaction?
Well, that's what I was going to go to.
Well, come back to my other question, which is, again, singularities are usually the kinds of things that we teach our students. Throw away the solutions that are singular. Those are the non-physical ones. Well, so how do people react here?
You see, of course, there were people who didn't believe me. I had remember a letter from Jim Bardee's son. Well, you know what his name is. Jim Bardeen, yes. Not the one who got 2 Nobel Prizes.
Okay. Yeah.
Jim Bardeen, yes. No, he wrote me and told me that my proof was all wrong. So I had to tell him, no, you misunderstood. There were people who thought it was wrong.
Technically, there's an error, or they were just saying we don't believe it. I mean, like a technical error they were claiming?
I don't think they just didn't follow it.
Okay.
There was one very good reaction, which was from Charlie Misner, who actually gave me a better proof.
Really?
So there was one part of my proof which was messy. And he said, why didn't you do it this way? I knew that argument. I just hadn't thought of using it. So I said, no, thank you. I hadn't thought of that. So my later descriptions, not the one given in the paper, my later descriptions used Charlie's improvement.
Right.
That was just a technical point, which made it better. It didn't change the argument particularly. It made a much neater way of doing it. So that was that reaction. But let me give you another reaction. I remember I was in Princeton. This must have been following that. And I remember going into the lecture room in Fine Hall or wherever it was there. And Bob Dickey came in and slapped me on the back and said he was very pleased with the result. Oh, you've really done it now. You've shown general relativity is wrong.
Yeah.
So a lot of people, that was their reaction. Yeah. Because you get these singularities, general relativity is wrong. And Bob Dickey was very keen on this because he had his own theory. Yeah, sure. The trouble is that the theorem works in his theory too. Right. So it wasn't much of a resolution of his problem. But
so go back to Einstein. I mean, so Einstein was highly skeptical of Schwarzschild's solution and so forth.
Of course, he died by then, unfortunately.
He died by then, but he was highly skeptical. What do you think Einstein's reaction?
I think he would have thought general relativity is wrong.
Really?
I suspect. I mean, there was quite a lot. Yeah, I remember also Phil Morrison.
Yeah.
I remember talking to him about it, and he said, "Oh yeah." I mean, he didn't believe in black holes and all that, and he thought it was wrong, and general relativity was wrong. I didn't realize he thought it was GR was wrong.
Yeah.
But it wasn't such a well-established theory at that time. I think. Right. I mean, of course, there was the Nobel Prize won by Taylor.
For pulsars. Yeah.
Yes, that's right.
Yeah, for the spin down rate.
That's right. Spin down. I mean, that was impressive because that really showed that it agreed with GR and gravitational radiation.
Hulse-Taylor, yeah.
Yeah.
So had Einstein thought of your argument back, say, in 1915 or so, he might have discarded the general theory of relativity.
That's an interesting point. It took a long time before people were, you see, there was a long time before people really thought you got right down to that level. It took the quasars, you see, really. Well, you have to go back to Chandrasekhar too.
Yeah,
because
sure.
there were studies of, that was the work Chandrasekhar did on the boat when he was 19 or something.
Going to Cambridge or something from India or something.
He was going to Cambridge, yes. Yeah. And he did this calculation to show that white dwarfs were unstable if they were more than about 1.5 times the mass of the sun.
Right, they would collapse in on.
Yes.
Yeah.
So he already showed that, and he realized there was a problem. And I think in his paper, he was very modest about it. He just said, this leaves us pondering on other possibilities or something like that.
Right. So now, obviously, you didn't think that this proved that the general theory of relativity was wrong. You thought this was just revealing a quality of the theory.
Yes.
Now, black holes were not yet called black holes at that point. But how did John Wheeler, the man who coined the term black hole or popularized it, what was his reaction to your proof?
Oh, he was very pleased with it. Yes. No, I think he thought it was No, I think people who were really into relativity and weren't prepared to give, I mean, they were obviously prepared to give it up in the sense of arguing that when you reached a level when quantum mechanics had an impact on GR, and that you might expect not to happen until you had radii of curvature of 10 to the minus 33 centimeters. So you're looking at 10 orders of magnitude smaller than an ordinary particle.
Right.
10 to the minus 13, 10 to the minus 33, what are we talking about? 20 orders of magnitude.
Yeah, well, it depends. If you call 10 to the minus 18 or so, maybe the radius of a proton, then you're looking at 10 to the 15 orders of magnitude smaller. But yeah.
Yes, sure, that's right. 10 to 15. If you're looking at sort of nuclear forces, and well, sure. That's right. So you're looking at tiny, tiny things way beyond the sorts of physics we're worrying about normally. Right. But if you have a gravitational collapse, then you're faced with this sort of problem. You will, is that what goes wrong? And in my paper, I just say, oh, well, something goes wrong and we don't know what it is.
Right.
And I think I can't remember what I said about quantum. Yeah, I did say.
Yeah. You did mention that quantum mechanics might be the resolution to it, but your paper wasn't black holes per se. It doesn't talk about event horizons. It's really talking about the inevitability of these singularities. So were you thinking black holes as the place where your theorem would really be realized in nature?
Well, that was the natural thing. You see, I remember giving a talk. Yes, well, that's another part of the story, of course. When I thought about the theorem in that paper, I gave a talk at King's College, London in late 1964. And despite what the movie says, Stephen Hawking was not there.
Oh, the Theory of Everything movie?
Yes, that's right. No, the person who was there was J.L. Singh, who was a distinguished relativist who had this very geometrical way of looking at it. I liked his book very much because it had this geometrical way of thinking, which was my way of thinking too. And he was there at the talk. He just happened to be visiting London, I think. I was pleased he was there. But the thing that worried me a bit is that it proved you had singularities, but you couldn't necessarily see them because they seemed to be hidden by this horizon. Didn't mean that they were necessarily, and you might imagine more extreme situations, such as a Kerr solution, which rotates. Yep. See, the normal rotating generalization of the Schwarzschild solution with rotation is the Kerr solution, and that's a nice exact solution. But you can have an angular momentum parameter and a mass parameter, and if the angular momentum gets too big, then you lose the horizon and you get what you call a naked singularity, which you could actually see the singular point. And the question arose, might you have those situations? Sure, you'd be likely to get the black holes, but there might be more extreme cases where you could get naked singularities.
Yep.
And the theorem I proved didn't distinguish between the two. It didn't say you necessarily got, I mean, you actually looking at the perturbing the Schwarzschild solution. So you expect that in those cases you would retain the the horizon, but there might be other cases where you didn't necessarily, it was worse than black holes. But I think I postulated this thing that I call cosmic censorship, which was that black holes were, forbidden to be seen. They were censored by the horizon.
Right. Now, that has not been proven, right? I mean,
don't think it's proved. No, I think it's still a generic.
Yeah.
In generic situations.
I remember I went to a talk 20 years ago by Saul Tucholsky, where he was doing work on these prolate ellipsoid mass sources for gravity. And he claimed that you could have the singularity popping out beyond the horizon. But then I guess there's been more recent work which has shown that that's actually not true in that case. So
yes, but I think you can get particular solutions. Well, the horizon in order from the charged, the charged version of the Schwarzschild solution, the horizon and Nordstrom solution. If it's like the curve with too much rotation, here if you have too much charge, then again you get a naked singularity.
Right. The question is, can these ever be realized? Yeah.
You get solutions, but the question is, are they generic? Would they survive general perturbations?
Right.
And that's what's not proved.
Right.
And the Tucholsky thing certainly doesn't violate that. As far as you say, I don't think it's yet established.
Right. So as observational work progressed, and Andrea Ghez, who has won the prize with you, as the observations began to establish the existence of black holes, did you feel vindicated? Like this is?
Yeah, I think so. I was really glad to see it. I think, well, the earliest, what was the earliest one? I forget. There was the double star, wasn't it? Which looked as though it was a black hole.
Oh, I'm not even sure I know what that one is.
There was the double star system, which was the first persuasive indication. Yes, it's sort of sucking. There was a red giant or something.
Yeah, and it was accreting onto a smaller mass, and
you could see the effects of the accretion.
I see.
It was pretty. You see, I used to go to these Texas conferences often.
Sure. Yeah, I went to one of those once.
I went to the first one that's where Roy Kerr talked about his solution.
Right.
But then I think it was stimulated. It was really the Engelbert Schocking, Ivor Robinson, Alfred Schild got together and said we need to bring the relativists and the astrophysicists together, because there really evidence for the general relativity playing a big role in GR. It was still, a lot of people were skeptical of it for a long, long time, but I could see they used to invite me often, several times at least, to give talks on black holes, which I did a few times. And it was nice to see how gradually, at the beginning, people were very skeptical, I think. It was a very small minority who really thought these things were really there. Yeah. And then gradually they built up, and you could see until it was about 50%, and then zoomed off to the other side. The majority of people were accepting them after that point.
Right.
It took quite a long time for them to pick up on them, yes.
And when the Event Horizon Telescope actually showed what we like to call a photograph, presumably that's pretty stunning moment. You spoke about elation as your experience of this idea that you were able to thankfully reconstruct. When you got the call about the Nobel Prize, was that also a moment of elation, or is that a different?
Quite curious combination of things, which kind of spoiled the event by the time I heard about it.
Oh, really?
Well, yes, because people ask me, what were you doing? What were you wearing or something? But actually, I was probably the first indication was I was in my birthday suit, because because I was having a shower, and the phone rang, and this was Petrona, who's my PA, and she told me she just had this strange phone call from somebody who wanted to know my phone number, and she said, I don't give out your phone number to strangers. And so, what's it about? And they wouldn't say what it was about. And it was somebody from Sweden, you see. So she slightly smelt a rat, I think, and said, well, is it about a prize? And she said, I can't tell you anything about it, I'm afraid.
Yeah.
But she wanted my phone number. So then I called Petrona back, and she said, I said, well, look, you might as well give her the phone number, because if you give it to me and I phone her, it's not any different.
Sure.
So then a little while, I waited for a bit, and then I got the phone call, and it was from a woman. She said, well, the president of the Swedish Academy of Sciences wants to have a word with you. And so would you hang on for a bit? Then she said, well, I'm afraid he's not available at the moment. I think he was trying to get hold of the people in America and Germany.
Right.
But she sort of hung up, and then the phone rang again, and this time it was the president of the Academy of Sciences, and he started talking to me a bit. And then in the middle of the conversation, he hadn't mentioned the Nobel Prize yet. In the middle of the conversation, he said, oh, excuse me, I think I have to, can you hang on? So I hung on the phone. I just waited and waited and waited and waited and waited. I said, I don't know what this is about, but if it's important, you'll call me back. So I hung up. And then he did call me back eventually. He told me it was the Nobel Prize. But by then I was beginning to get pretty suspicious about all these things.
I wonder if you're the first laureate to ever hang up on the...
I don't know. No, it was quite a long time. I mean, if it had been only a minute, I was being on still. It was several minutes, yeah.
That's fantastic. The ceremony has not yet happened, or they're doing it by Zoom, or Andrea told me.
I don't know how they do it for most of them. In my case, since I'm the only one who's actually resident in UK, there are three other British. Is it two in chemistry and one in no, one in chemistry. I've gone which way around.
Numbers, yeah. Sorry.
There's two. There's biology, isn't there? There's biology and chemistry.
Two biology, which would
biology,
be Jennifer Doudna, Charpentier.
Right. But they're all elsewhere. I think they're in the US. So I would have been the only one.
Yeah.
So they are giving me a car to take me down next week, and to the embassy or the residence of the ambassador. I see.
Okay.
So down with my wife and my son.
Very nice.
And that'll be the audience, I guess.
Yeah, it's an unusual time, unfortunately, but it doesn't take away from the honor in any way. And congratulations on that. Can we shift gears to talk a little bit about cosmology? Is that
sure? Yeah. Well, it's a natural progression.
Yeah, it is, of course. I guess so. I guess to connect the dots, I guess Stephen Hawking, who wasn't actually at that lecture, but certainly at a subsequent.
Yeah, well, I should continue that because Dennis heard about the lecture.
Yeah.
And he got hold of me and said, "Would you like to give a repeat in Cambridge?"
Right.
So I did. So this was in early '65.
Right.
Then Stephen was at that talk, and more importantly, I had a private session with Stephen and George Ellis, maybe Brandon Carter, I can't remember, but certainly George was there. And so we had a long session together, and I talked about the details of the methods I was using. And Stephen picked up on it very quickly. And the first thing he did was to use my exact theorem, but in the reverse time direction, and using not for local, but for very far off.
Right.
And it was a clever idea. I hadn't thought of using it. I was thinking of it as a local. Doesn't have the power when you use it at a distance, because you have to assume you have a Cauchy surface which is space-like, which is non-compact.
Right.
And of course that's less. I mean, for a local thing, you can assume it goes off to infinity, so that's fine.
Right.
But for a cosmological model, it doesn't have quite the force. So Stephen then developed the techniques and made many advances on these techniques. And he had a lot of help from Brandon Carter, I think, because occasionally there were mistakes in the argument. There were what I call mistakes of the first kind, not mistakes of the second kind. That is to say, you just find a new way around them and it's fine, still works.
Right.
So there were never any mistakes of the second
fatal
kind.
errors, so to speak. Yeah.
Yes.
Right.
And there were some even in the thesis, which was Dennis and I were examiners of him. And
you were examiners for Stephen's thesis?
The two of us. It's not like in the film where Kip Thorne was there. Kip Thorne was not there. No, it was just the two of us. but there were a few mistakes, but I was going to point them out to Stephen in the oral, but he'd found them all already. No, it was an amazing piece of work. He'd done 4 different topics. And I said in the account, well, any 2 of them would be good enough for a PhD.
Right.
But the last one was on the singular. Only the last one was on the singularity.
This is now cosmological singularities.
Yes, so he'd worked, and then we got together. He did 3 papers in the Royal Society, and there were certainly significant advances, particularly on the getting rid of the Cauchy surface condition, which I think was perhaps the most significant thing he did, looking at Cauchy horizons and their properties. And no, I think he did a lot of good work on that. That's clearly true.
So the general conclusion was that under fairly generic conditions, cosmology would have to have a Big Bang-like singularity, much as a black hole has a central singularity.
That's right.
Right.
So we can, yes. Well, the next part of the story, as far as I'm concerned, was I was in Princeton. You see, I was in Princeton, and we were about to go off to a meeting in Stevens Institute in Hoboken, just across the river from New York.
Sure, yeah.
And lots of people from New York State were I mean, it's a thing that was they were going on for many years. They're important meetings. And people from Princeton were going up there, and you had to drive up in various cars. And I noticed in the back of one of the cars was, in the middle, I think, was Jim Peebles. And of course, last year's visit. And of course, this was a long time before that. Sure. And I asked him, I said, since I took the opportunity of asking him a question, there was no room in the car. I didn't go up with him. But I said, why don't there's all these different solutions you come up with, much more complicated than the ones you consider in cosmology. Why don't you look at all these other complicated kinds of models? And he looked at me and he said, because the universe is not like that. And I thought, my God, it's not like that, is it? I think he was thinking about the cosmic microwave background and the evidence of how uniform it is.
Right.
And so it's a singularity of great uniformity. It's not like any of those messes. And this was a moment of revelation to me, because I thought, gosh, now you've got to explain why. Up to that point, it was, as you say, the arguments for singularities work just as well in the future as in the past. Future singularities, past ones, future's black hole singularities, past ones, Big Bang.
Yep.
But it's very different. And the idea would be it's quantum gravity. It solves the problem, and blah, 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 blah. But then that doesn't make any sense. But if it's quantum gravity, why does quantum gravity tell you you've got this extraordinarily uniform initial state and this great mess of, and it's all tied up with second law of thermodynamics.
Sure.
And this is a clear point, that the uniformity means that the gravitational degrees of freedom were not activated. And that's what drives the second law of thermodynamics. It's really fundamental to physics.
So highly ordered gravitational degrees of freedom that then can become disordered.
Yes, well, it's the Vial curvature. So this is again the Vial curvature. If you think of Vial curvature as describing gravity, which was not really the way many people thought of it, but that was the way I thought of it. Vial curvature is the gravitational field, and that is 0 at the beginning. I mean, we don't know if it's exactly 0, but it's suppressed.
Right.
And the fact that you get this uniform Vial curvature 0 initial state, and then allows you to have the potential to clump into clouds of gas, stars, galaxies, sun. Sure. And we get our energy from the sun in a low entropy form. I mean, that's the whole point that Schrodinger pointed out very crucially. We don't get energy from the sun because it all goes back again, apart from global warming, but that's a small effect. We get as much energy from the sun as we shoot back out again. But the difference is we get it in a low entropy form and it goes out in a high entropy form. So it's a small number of photons coming in, spread out over many, many photons going out.
Yeah, I think 20 times as many photons out as come in typically.
Something like that. And that's really what we live off. It's the entropy in there. And that's because the sun is a hot spot in a dark sky. And it's a hot spot in the dark sky because it clumps from gravity. And that's where all life and everything, it all comes from, this fact that we have this low entropy in gravity, even though it's high in everything else. So I had no idea why this is. And I thought, gosh, it must be some very peculiar theory of quantum gravity, because it's some very peculiar theory, which is so grossly asymmetrical in time. That was the view I held for a long time, and it must mean that the theory is crazy. Well, probably crazy anyway, but very crazy, because it's so different in the past and the future.
Right.
And then I formulated this thing called the Vial curvature hypothesis, just a hypothesis, just says in singularities in the past type, pretend there aren't any space-like ones, that would be cosmic censorship violated. Then you've got two kinds, past kinds, future kinds, and just different. Future kinds are a great mess. Vial curvature running wild. Maybe there's where Kalatnikov and Belinsky and Lifshitz are right. Quite possibly. I don't know if they're right or not. It's quite possible. But absolutely wild kind of behavior.
Sure, in the future.
Absolutely crazy. And Misner did the same sort of analysis. And that's very possibly the sort of thing you get. Why is it so different? Is it just quantum gravity, crazy quantum gravity, or is it something else?
Right. Now, while this is going on, we're developing more conventional cosmological ideas. I'd love to hear about your more maverick recent thoughts on how to incorporate this into cosmological. But can I first have your thoughts on the inflationary cosmology? You and I have actually had conversations about this in the past, and I know that you don't solve anything.
I heard about it, and it just made me feel ill when I saw it, because, well, I mean, I knew it. You have this problem. I mean, my outlook on it was different from other people's. You see, I think many people were worried about the scale invariance of the
cosmic background radiation,
which is a big feature, and they couldn't see how to explain it, and that's sure. And inflation was an attempt to. That wasn't the main reason it was put forward initially, but never mind. It was certainly something in its favor, but it was, to my mind, a very ugly theory, if I may be allowed to say that, because you had to invent this field, the inflaton field, which had this very specific, it only was invented for this one purpose. Sure. It had to have this peculiar kind of shape of its potential curve, and it just to make it do this, what you're supposed to do. And it didn't solve my problem, which you could see quite easily, because you just think of collapsing universes, and you can put an inflaton field in just as well, reverse time, and
all sorts of wiggles in it.
It just never solved the problem.
But Roger, let me ask you this. So many people in inflation view the inflaton field as more of an existence argument or a toy model for a cosmology in which you'd have repulsive gravity early on because of the pressure being sufficiently large, as we were talking about before. And so the real quality of inflationary cosmology, I think most people hang their hat on, is a period of accelerated expansion in the early universe, regardless of how it comes about, the inflaton field just being one toy model, if you will. That doesn't resonate with you at all, though. It doesn't help you, no.
I mean, you could put that in, whatever it is, and then you see, you get this mess at the end, and nothing. I mean, it doesn't work. I mean, unless you put asymmetrical physics in. I mean, time asymmetric.
Time asymmetric, right.
No, okay, then my claim, my argument would fail. But I didn't see that in any of the schemes that people have put forward. They'll just say, well, you know, when the curvatures get big or blah, 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 or something.
Right.
But that's not telling you anything. Which
I guess most people would say we put in, you know, the so-called past hypothesis that for reasons that we can't really explain, you had low entropy initial conditions. And of course, that's the puzzle that one wants to explain. And then if you imagine that there's accelerated expansion forever into the far future, then you get the time asymmetry, not from the fundamental laws, but from the solution, where you'd have this.
I know, but you're choosing, this is my picture of the deity putting a pinprick into the
one little pinprick in the 120 possible
10 to the power 10 to the, that's 2 10,
yeah, of course, sure,
10 to the power
10 to the 120, yeah,
124 or whatever it is, yes,
yeah.
Sure,
yeah.
Well, that's I mean, that's just, you need a theory, you don't need a No, it just seemed to me that's the wrong picture.
Right.
But I thought you had have a crazy quantum gravity. I didn't like the idea, but I couldn't see. I thought it probably you needed for just make the reduction of the state vector too, which you probably do, but that's not with a crazy theory like that.
Right. But what about the idea, and I'll come to that in a second, what about the idea that people like Andre Linde and others have developed in various guises, where you imagine that early on, you had some chaotic state where the inflaton field might be wildly undulating, and it just so happens that in a tiny region, maybe 10 to the minus 27 centimeters across, the inflaton field just happens to get a uniform value, allowing for the negative pressure that can drive the repulsive gravity. What about that idea?
Well, I described this in my book, Fashion, Fact and Fantasy. Yeah, I got this initial state, which is all like that. And occasionally you get this little tiny smooth bit.
Right.
Okay, what's the likelihood of that? Well, you've got 10 to the 10 to the 10 to the minus 24. Okay, well, how about making a universe which is only about as big as our galaxy?
Right, that's even more probable. Right.
It's much, 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 much more probable than the other one.
Right.
So if you're going to do it by that argument, why do we see our universe keeping on going? It's not just done for our galaxy, our life.
Yeah.
It's on going and going and going.
Right.
And it doesn't even help to make, you could say, okay, well, you maybe need lots of them to get living human beings or whatever.
Sure.
It
totally makes sense. But again, some would say that maybe one's being too quick in conflating small measure with small probability. I mean, because certainly in the space of all possibilities, we're talking about a set of very small measure to give rise to the universe in that formulation. But how do you know that small measure means small probability? There could be some other fundamental principle that
well, you could have something guiding the creator's pin into this small measure region for some other reason. Sure, you might have, but it's not the right theory. Not a theory. You need a theory for that.
Yeah. So tell us what you've been thinking about.
Well, you see, this was the other ingredient to this discussion. Again, I was thinking, you see, I had this picture of infinity squashing it down in the future to make a nice description of, and I was just thinking about how boring the universe is in our picture. Okay, it's exciting now, all sorts of interesting things going on. Some of them nice, some of them horrible. But it's, think of the remote future. Well, these supermassive black holes will swallow up entire galactic clusters, and then they'll drift away from each other. And you just get these black holes, they sit there and they sit there and they sit there. Eventually they evaporate away by Hawking effect. I mean, it's already pretty boring when you've just, I mean, some people say black holes are exciting, but you get bored with them if that's all there is in the universe. And they just drift away from each other. And then they evaporate by Hawking. Then that's really boring. So then I thought, well, who's going to be bored by this universe? Not really. It's only mainly photons running around. That's most of what's running around. And these photons don't get bored easily, not just because they don't have experiences in the ordinary sense of the word, but because the time progression is zero for a photon. It gets from here right up to infinity to it in zero time.
Right.
So it's at this boundary, which is infinity, it reaches it, and I said, well, maybe there's something on the other side of that boundary. Well, it's in the asymptotically flat, it's null. But if you've got a cosmological constant, so being convinced of the cosmological constant, which took a little while for me because I had wrong reasons for disbelieving it. And I think it was Jerry Ostreicher who persuaded me. I remember we were going into dinner somewhere, some college, and I said to him, well, all this stuff about the cosmological constant, maybe it's just dust or something like that. And he looked at me and he said, that's not the point. Putting positive lambda in there solves an awful lot of problems in cosmology. It makes lots of things come together. So I thought, okay.
Accelerated expansion, CMB, the critical density, it all works together.
It works so much better. Yeah. So I thought, okay, you win. Cosmological constant. So that means space-like, infinity is space-like. So now I knew it was space-like. Now a lot of photons come and they hit this space-like surface. What's on the other side? Now I should explain, just going a little back, I had this Vial curvature hypothesis for the initial Big Bang, but my student, Paul Todd, who had been working on these things, and he thought a much nicer way of phrasing this was not to say that, but to say, because it's unmanageable really, because you could say that the Vial curvature at a singularity is 0 is a mess, because if it's singular, everything's going wild anyway. To say it's infinite 0 at the same time doesn't make much sense. But if you stretch it out by this informal stretching to make the Big Bang into a nice finite boundary, infinity makes, by theorem of Helmut Friedrich, you can see that future infinity isn't going to be nice and smooth, space-like. By the past, okay, let's postulate that it's nice and smooth. It doesn't quite give you the Vial curvature hypothesis. It makes the Vial curvature finite, but that's not bad. But then I thought, okay, let's adopt that picture. And now when you match them, it makes the Vial curvature 0, because by Helmut Friedrich, well, by various arguments, it's got to be 0 on future infinity. And so if you match this to the Big Bang, then it's 0 on the other side. Now you see this is completely crazy, because on the one side, you've got very, very rarefied, low density, cold, colder and colder and colder and colder.
Yeah.
On the other side, you've got enormously hot density, enormously hot, completely the opposite. What right do I have to match the two?
Right.
Now the argument is, and there's a bit of hand waving in this, but okay. In the future, here's where most of the hand waving is actually. In the future, it's mainly photons. And photons have no mass. Photons respect the conformal structure.
Scaling
Maxwell's
structure.
equations, yeah. Maxwell's equations don't notice if it's squashed or not. The equations are conformally invariant.
Sure.
So that the Maxwell field becomes perfectly finite at infinity. Photons are fine. What about the Big Bang? Well, now it's the opposite. You have a very, very hot situation, and now you're stretching it out. The squashing of the future infinity makes it warmer again, if you like, more dense and warmer. The stretching of the Big Bang makes it much, much colder and less dense. Why are you allowed to do this? Because you've got massive particles. No, you haven't. Because the particles, when they move around faster and faster and faster. Then by Einstein's E equals mc squared, this tells you that the energy in the radiation, the mass, if you like, in the radiation, completely dominates. The mass is now completely irrelevant.
Right.
So the particles in the Big Bang are effectively massless, which you get right at the beginning. Right. So there, again, they respect the conformal geometry. So the future and the past, if you take this view, and this is where it's crazy, but all crazy things have been right in there. I mean, you look out at the sun, you see, well, it moves around the sky. To say that the Earth is moving, not the sun, I mean, that's crazy. And it's right.
but what if you have some massive particles hanging around in the far future?
Yes. I mean, as people have said to me, I remember Gary Gibbons saying that was the weakest part of my theory. I said, well, yes, it is the weakest part of my theory, but if that's the weakest part, I'm quite happy. Now, what I say is that, and there is an argument for this, and it needs more working on, but the sort of argument is, what's the first thing people do in particle physics when they classify particles? What they do is they look for what are called the Casimir operators of the Poincare group. Now, there's a little bit of jargon here. Sure. The Poincare group is the group of symmetries of special relativity. Now, what are Casimir operators? Well, these are things which are completely conserved. And one of these, in the ordinary theory of particle physics of special relativity, you see particle physicists usually consider the physics. They don't talk about gravity, you've got special relativity. And you've got these Casimir operators, which are absolutely conserved, are mass and spin.
Yep.
Now, when you've got a cosmological constant, you might argue that this isn't the right group. The right group, you put the cosmological constant in, it doesn't really play much of a role until you've got this exponential expansion starting to come in. And then the group, maybe you could say, it's not really the Poincare group, it's the de Sitter group. And you look for the Casimir operators in the de Sitter group, and you see that mass is not a Casimir operator. Now, this argument is not a terribly strong one. It's just, for me, it was where I say, okay, I don't have to take current particle physics that seriously to say that mass has to be an absolute constant over huge cosmological timescales. And I would argue, for various reasons, that the lifetime of the dark matter particles, you see, this is going a little ahead of myself here, but you have dark matter as the main constituent of material in the universe, that the dark matter particles would gradually decay, and their decay would have a lifetime of about 10 to the 11 years. So that's another 10 times
the age of the universe.
Age of the universe. So that's about the lifetime. And these things would then decay. But you also have to have a mass. This is just particles decay. I'm not arguing that the massive, you see, electrons would have to lose their mass. They can't decay because they've got charge.
Right.
And so they would have
electron positron annihilation, but you need to get rid of everything.
That's right, but they're not going to. They can't meet each other. They get separated.
Yeah.
And you get hydrogen. No, the idea is that the mass itself would have to fade out very, very gradually.
Right.
That doesn't have a proper theory as it stands. So I would say Gary Gibbons is completely right. That's the weakest part of the theory. But if that's the weakest part, I'm quite happy. We need to work on that, and we need to see how the proper theory of particle physics in this cosmological context really works.
So in this approach, you really do imagine then that it's a cyclical process where the far future attaches to the far past.
But not it's a different person's far.
Right, different person far past. So in terms of predictions for things that you might see if this theory is correct, I know you've written a few papers over the years. Yes. What's the state of things now? I know things have been, is it settled? Do you have a sense of what one would look for?
I can think of three observational features. The first one was the first one. The first one that I thought about was
the circles in the CMB.
That's right. This is the collisions with supermassive black holes.
Yeah.
So if you have a galactic cluster, then the galaxies in the cluster, assuming that each one has a supermassive black hole in it, they will gradually collide with each other. We will collide with Andromeda in a little while, a few thousand million years, I guess. And probably they will, galaxies, black holes will spiral into each other, and there will be one walloping explosion. Mostly energy will go out in the form of gravitational radiation. This gravitational radiation will make its mark on the crossover between one eon and the next. And this mark will...
Eon is a cycle, is that what you call a cycle? Yeah.
Yeah, I call it eon, A-E-O-N. I looked up in the dictionary to see how long an eon was, because I didn't want to, if it was a certain number of years, that's no good.
Right.
It wasn't a certain number of years. So I thought, okay, I'll call it an eon. And I like to spell it with A-E because that looks fancier.
And that's a choice that's allowed in the dictionary, I guess.
Oh yes, that's an allowed spelling. Good. So the eon starts from the Big Bang and ends with this remote future squashed.
Right.
So I've now made it into this compactified version. Big Bang stretched to remote future squashed. That's one eon. Then there's a next eon, somebody after us, and the next one, and the next one. And there's one before us, and a black hole explosion of these, this is a collision between two black holes, form this basically an impulse, because it's in the sort of timescales we're talking about, the spiraling in is almost impulsive.
Yeah, right.
You have this great impulse coming out, hitting the crossover. This will cause in this crossover surface, well, you've got to wait for 380,000 years before you actually see the effect of it.
Sure.
And that's Jim Peebles' work, basically, with his colleagues in various places. Nobel Prize last time. Yep. What you do from Big Bang to 380,000 years. And at point, the Big Bang stretches out to about 8 times the diameter of the moon here. Now the rings would encounter this, well, they'd be coming out, and they would start to Well, they will disperse a little, but they pretty well remain a delta function, I think. Yeah. And so you look back at us and you see this heating or cooling. It depends on whether it's, I mean, it's counterintuitive in a certain sense, but the most distant ones would be blue shifted. That is, the signal is coming towards us.
Yep.
And the closer ones would be red shifted. The signal's going away from us. That's the way the geometry works.
Got it.
So that
there's hotter and colder circles in the
that's
scene.
right.
Now,
so
people have looked for those, right? So my understanding is that they haven't found.
Some people have looked and found them. Some people have looked and haven't found them. It's easier not to find them than to find them. I'll tell you that.
Right.
Well, you see, the first people to look were David Spergel and in Princeton.
Yeah, I remember at the 2000.
That's right. He had a look and he got Amir Hajian to do the analysis. They looked at it in a way which I learned later was not terribly appropriate, but they started to see signals at first and then they realized this was not right. And then they got rid of them and then they didn't see any evidence of signals. I think that's quite fair. I suggested twisting the sky at that point, which was a way of seeing whether the signals change. I thought there was a slight change in signaling, but it wasn't quite what I expected. So I didn't make any noise about that. I agree that they didn't see any signals. Right. But then a little later on, Vahe Gurzajan, who's an Armenian, who I knew from other things he'd done, and he'd showed me that he'd looked for low variance rings. But the difference in the way he'd looked at it, you see, the way that Spergel and Hajian had looked was to look for over the whole sky, consider a radius ring, and then look at the temperatures and see whether there's non-Gaussianity in the something non-random about the temperature over the sky. Sure. And when they corrected for the things that were wrong, they found that there was no evidence for this. That's true. I'm not disputing that. Right. But then what Vahe showed me, he was doing it differently. He was fixing the center and then looking not for higher or lower temperatures, but for lower variation in the temperatures. And he considered to have found a signal. I see. And then since he was looking at fixed centers with different rings, I said, well, look, if you're doing it that way, maybe you will see several rings with the same center. Because they would see if it's the same galactic cluster, that galactic cluster will compress into one point from our perspective. And if these collisions come several times, maybe one supermassive black hole swallowing lots of others, or several explosions in the same galactic cluster, whichever it is, they would be centered at one point. So you've got concentric rings. Got it, right. So he then looked for concentric low variance rings. And there was a lot of fuss about this. His analysis was done initially in a way which was not considered appropriate. And I think it was right, probably, not to consider it appropriate, because he had not appropriately taken into account the usual procedure that people use, which is to put in the curve of the what's called the power spectrum. You see, what you do, how do you know that an effect is real or not? Is it random or is it real? Well, you make a comparison with a lot of fake skies. So you make 1,000 fake skies or something. Now, how do you know whether the fake sky is a proper fake sky? Well, you say it's a fake sky which fits the same power spectrum. That's the dogma. I mean, it's okay. It's a pretty good dogma. At least you can use it, sure, and you can vary. That's you see, for each harmonic, you see all these different. You imagine the sky is like a drum, and it vibrates. And it has different. There's an overall way of vibration, which is called the L value, and within each L value, you've got the M values, which are the details of it. And the power spectrum is looking at the L values. For sure. You can use this L value and then vary within the M values. And Vahe hadn't really done this initially, so they were right to criticize him on this. But then he did do it this way eventually. And I can't quite see why criticisms are there. And he then tested this for twisting the sky. That was, I thought, quite a good way of doing it. You could see that when you twist the sky, that the effect starts to go away. And the more you twist, the more it goes away. So it favors circles. I see. But then the Poles, and when I say Poles, I mean Christoph Meissner, Pavel Nurowski, and I forget another Pole who did the analysis on the computer analysis. They looked at the we'd only looked at WMAP data. They looked at the WMAP data. That's the first of the satellites which you really could look at the variations in temperatures.
You looked at Planck now, or?
Then we looked at Planck. Well, I should say that the Poles looked at WMAP and they found an effect. And they gave a probability of the effect, which was 99.4%. This was in the Planck data. I think in the WMAP data, it was 99.6 or 7, I think. Confidence level. So it looked as though there was something there. Everybody ignored their paper. I'd never seen any complaint of the analysis they did. Then they did it for the Planck data, and they found a 99.4% confidence level. And Abahe and I did it a different way by looking. There we had a lot of trouble with referees and so on. And
but your claim at the moment is that this theory is alive and well, and perhaps there is even.
Well, I should go to the next effect. You see?
Yeah, please.
Because this was all the colliding black holes.
Sure.
Then at one point, I was talking to Christoph a bit, and we talked to where do we go from here? And we decided we'd look for. I'd never dared to look for the Hawking points before. You see, what happens to supermassive black holes? They are, well, it may take 10 to the goodness knows how many years before 10 to the 103 years, I think, is what Don Page.
For a few billion solar mass black hole, 10 to the 100 years or so.
Yes, Google years or something like
Google
that.
Years.
That's a pretty long time.
Yep.
And in that length of time, the radiation these biggest black holes will evaporate entirely away in terms of black hole, mainly photons.
Yeah.
Now, what does that do in the crossover? Well, you just see what happens. It's squashed into a little point. It's useful to imagine these Escher pictures with angels and devils. So that's a nice conformal map, and you can see what infinity looks like.
Everything gets squashed at the edge.
Right. Yep. And so all the radiation gets squashed in this little teeny weeny point. So all the energy of that black hole, or the mass in that black hole, is squashed into that little point. Now, I never faced up to this because you talk about singularities. That's a singularity in the crossover. Everywhere else, you've got nice, smooth equations, and you could tell what happens as you go across. But here, you've got one singular point. So you might throw up your hands. But you don't throw up your hands because you can tell that there's a mass there by doing an integral around it. So even when you cross over into the other side, you can't get rid of there being a mass there. So it doesn't depend on what theory you have of what happens to this radiation in the crossover. So it'll be quantum. That's where quantum gravity really makes its mark. But what it doesn't make much difference. It's just a burst of a huge amount of energy in that tiny little point. Now that spreads out to 8 times the diameter of the moon. This is the standard stuff that Jim Peebles and his colleagues worked out for the 380,000 years. So 8 times the diameter of the moon, you should see slightly warmed spots. Okay, well, we have this paper out, I don't know, about 6 months ago or so, in the monthly notices of the Royal Astronomical Society, where we claim at 99.98% confidence level, this is using Christoph's analysis, these points are there. Also, this is in the Planck data. Also, if you take the 5 strongest points and you look at where they are, you look at the WMAP data and you see points there in exactly the same places. You find another one in the WMAP data and look back in the Planck data and it's there in the same place. So you have 6 points, which I think are genuine. I'm not sure whether the weaker ones are genuine because the analysis, which gives you this high degree of probability, is only overall. It doesn't tell you that for any particular point.
Right. Have you heard from the microwave background experts around the world on this paper?
It's a strange kind of conspiracy of silence. I remember talking, this is before this paper, I talked to Christoph about this. And I said, I think he said to me, how much response do you have on your paper in the European physical paper? I said, 0. How about you? And he says, 0. So it's a conspiracy of silence. But then it's not quite zero in the sense that there's the papers by Douglas Scott and collaborators, and they looked at the rings, I think, and claimed I was glad for them to look at the rings because they found the pictures looked almost the same as Vahe's. Pretty well exactly the same. So they found the same distribution of the rings, and then they waved their hands and said, "Oh, well, it's not. It's only random."
Right.
But it's not random, even if you just look at it. Particularly if you look at the centers. You look at the centers of the points in the Planck data. That's what's most distinctive. And what's more, this is I found very striking, is what's more, not only are they clumped in certain regions, but they're clumped in temperature. Now, the temperature gives you another parameter in Vahe's analysis, because you look for them for low variance, not because they're warm or cool. You look for them because the temperature variance around the ring.
Sure.
And you look for triples of rings of low variance temperature. And then you plot the centers. And they're clumped. And they're clumped in temperature as well as in variance. So if you look to the lower right-hand part of the picture, you see a great region of red spots. Red means warm, which means blue shifted, which means distant. I hope I've got it the right way around. So that's a very distant region. Mm-hmm. Technically, in standard cosmology, would be outside what we call our particle horizon. So you shouldn't even see them at all. But in this you can, because you're looking into the previous eon. You're looking further out than you can see into our eon. Right. At the top right, you can see a blue region, which is presumably within our I don't know, there should be some signal seeing in the micro background in our own, I don't know, I haven't tracked
Well, it's a curious state of affairs because, thinking science and sociology, blending them for half a second. So the inflationary theory has been the dominant view for a long time. Full disclosure, I have to say that I am certainly in that camp. That is the way that I've long thought about things. But even Paul Steinhardt, one of the inventors of the inflationary theory, has now moved on to create his own version of cyclic cosmologies. Right. And he now claims that inflation is not as secure as people claim it is. And now you've got another cyclic approach, which is again heading off. And again, I can't respond to any of the details of what you're referring to in the data. I'm not a CMB expert, haven't looked at the analysis, but it certainly is, if nothing else, it's an exciting time that there are competing approaches to thinking about the deep question of how the universe got to be and what the true nature of the world is. So
it is, I mean, I had these arguments against inflation before. That was pre this model. But this model, I think, really is hard for inflation to model because not just the Hawking points. I mean, you've got these really energetic points at the crossover in this conformally stretched Big Bang, and you've got to explain them. You've also got the clumping, both in temperature and in this region in the sky, which is surely goes against inflation because that says
of course.
And I think one of the reasons you say, why haven't people seen the Hawking points before? Because they're pretty obvious, probably.
Yeah, what do you think?
The reason they haven't seen them is just haven't looked. People haven't thought, well, they're not there because inflation says it must be very uniform. So why look for spots like that?
Right. I don't know, but the CMB folks are so fastidious and so careful in the analysis. But it'd be interesting to see where this all will go. Certainly exciting. Yeah, can we segue to a little bit of quantum mechanics, which is of course relevant to everything we've been talking about?
Oh, sure. Yes.
So quantum mechanics, among one of the two great descriptions of the world emerging in the 20th century, fantastically accurate predictions. You're of the perspective, and I have to say on this, I fully agree with you, and it's my perspective as well, that quantum mechanics is not a done deal. Quantum mechanics is not a full description because of what we usually call the quantum measurement problem. Yes. Do you want to describe that for a moment? Because I have a few questions on your perspective on the measurement problem, what it's telling us.
Well, my perspective, I know you shouldn't bring in names here, but Einstein, Schrodinger, and Dirac all believed something had to be done about quantum mechanics to deal with this issue. The issue is, I mean, people say quantum mechanics is the most wonderful theory in physics we've ever had or something. Well, it's a wonderful theory. I don't like to call it that wonderful because it's self-inconsistent. Now, what do I mean by that? Well, the Schrodinger equation tells you how the quantum state evolves. The quantum state is the way we describe things in physics.
Yep.
There's a slight caveat to that because one might say, what about the density matrix?
Density matrix.
So,
yep.
yeah, I mean, that's a little bit of a...
we can put that to the side for now. Yep.
Yes, put it aside. It doesn't solve the problem.
Right.
But the problem is that you've got this evolution of the quantum state by the Schrodinger equation. Beautiful equation, works wonderfully. When you can test it, it works actually perfectly. Then what do you do with it? Well, as Schrodinger himself pointed out, I mean, he was very clear on this, although people take it the wrong way, in my view. He described this cat in the box. He was really saying, look, you could have a cat in the box. According to my equation, that's Schrodinger talking, if you like, according to Schrodinger's equation, you could have an evolution of the cat in the box in which it evolved to a dead and alive cat at the same time. This is ridiculous. There must be something wrong with the theory. That was his viewpoint. But people pick it up and say, oh no, you could make it, if we had more and more better boxes, better cats, better experiments or something, you could make a cat in the box, which is dead and alive at the same time. But Schrodinger was really pointing out the absurdity of this situation, which I agree with. Einstein agreed, and even Dirac, although it's hard to find.
He was a man on a few words, so he can't.
A few words, and usually he was very careful of these words, that he didn't say anything that he didn't totally have a mathematical backup.
Right.
And this was the case. He didn't, but he did certainly. If you find the right place, you can find a good quote from Dirac.
Sure.
But he did say there has to be something wrong, because the evolution, as used in quantum mechanics, where you say evolve according to the Schrodinger equation, and then you don't say that the Schrodinger equation describes reality. You say make a measurement, and it tells you the probabilities. Well, what's making a measurement? Well, you wheel in out of the cupboard this machine which makes a measurement. Sure. That machine is made out of the same things as everything else. So why doesn't it evolve according to the Schrodinger equation? It doesn't make a measurement. It would say, doesn't say I see this or this or this. I see, well, particle here or particle here or particle here. I see this superposition of particle here, particle here, and particle here. And it may have a dial on it which says particle here superposed with seeing that particle here, superposed with seeing particle here.
Right.
But you don't see that. You see only one of them. So that isn't the way the world works. The world does not evolve according to the Schrodinger equation. It evolves according to this curious mixture of Schrodinger evolution, collapse of the wave function, Schrodinger evolution, collapse of the wave function. I mean, that's what quantum mechanics, when anybody uses quantum mechanics, that's what they do. They use this.
Of course.
And they say, well, I'm not clever enough to understand how quantum mechanics explains this. I just work ahead. Well, none of us are quantum clever enough.
Yeah, or we follow Niels Bohr and basically just say, we just use it as an algorithm for making predictions, and we're not actually describing the world. But you use the language inconsistent, and that was the point I wanted to pick up on.
Yes,
because other people use more polite language. They say perhaps it's incomplete.
Yes.
And so why do you say inconsistent as opposed to we still need to go further?
I think because people who say incomplete, nobody listens to them. So I'm trying to be a little ruder. No, I don't know. It is inconsistent because, I mean, I think they're just polite, you see. Incomplete. I guess probably, well, another way of saying things. Do you say Newton's theory is wrong or incomplete?
I say it's, you know, it's the right theory in a limited domain of reality, and then you go outside that domain and it fails and you have to extend your theory and so forth. But what I mean a little bit differently is here. So let's go back to quantum mechanics.
Yeah.
There are approaches. For instance, the Bohm-de Broglie approach to quantum mechanics. That gives an answer to the quantum measurement problem. It's a self-contained theory. It's non-relativistic, although some people say you can relativize, but let's put that to the side. Wouldn't that be a consistent version of quantum mechanics? Or would you perhaps not call that quantum mechanics any longer?
Well, I had long talks with Bohm when I was at Birkbeck College, because he and Basil Hiley.
Yes.
We and the various other people, we used to have weekly meetings. We had long discussions. So I did know about his point of view, but it was hard to pin him down. I always thought he was very much like a wave function himself. He was talk about something and he sort of spread out over the universe like a wave function. And you pick your question, you ask him a question, you see, and it would collapse on this. He'd give you a very precise answer to your question, and then it would start to spread out over the universe again like this. So I thought he was very much, in his arguments, very much like a wave function, which would collapse from time to time. But yes, I know there are all sorts of models like that, and the
PRW theory, which has a spontaneous collapse.
Sure, and I'm great respect of all these. I have great respect for all these theories. I think they're. I certainly would say, go with it, do it. But I think, you see, the thing I've taken advantage of the lockdown to do something which I never really worked on, which is to develop the few ideas I had on collapse of the wave function to see what more you can say about it.
Yeah.
And the thing is, I certainly think it's a gravitational effect. I think that's,
you do. Right.
I had a strong argument for that, which has to depend, I mean, it's a very limited argument, but it's fairly strong in its limited context. It says, you see, the fundamental principle behind Einstein's general theory of relativity is the principle of equivalence, which says that a gravitational field, at least in sort of locally, is equivalent to a free fall. I mean, Galileo, you imagine him dropping a big rock and a small rock.
Sure. Even
if he didn't actually do it, he certainly thought about it. And there's an insect on one looking at the other, would not experience any
fall. Yeah.
Now, this means there are two ways you could look an experiment. Say you're doing a tabletop experiment, a quantum experiment, and you want to take into consideration the Earth's gravitational field. One way is to put into the Hamiltonian, quantum jargon, but whatever you do, it's a procedure. You put in the potential for the gravitational field, just as though it was any other quantum field, and go ahead. Fine. The other way of doing it is say, no, that's wrong. You should imagine your coordinate system is dropping freely and there's no gravitational field. You do it that way. You get almost the same answer. Why almost? Well, the expression is exactly the same, except for what's called a phase factor. This is just a multiple wave function. You multiply by this thing, which is called a phase factor. Now that phase factor, you say when you make a measurement, you square it and it doesn't make any difference. But you look at it carefully and you see it's got in it the term involving the cube of the time, an exponential of the cube of the time, which means that you have what's called a different quantum vacuum. See, in quantum field theory, you have different kinds of vacua, and you have to settle on which vacuum you're using to make sense of your theory. But you should be consistent with your vacuum in order to have a consistent quantum field theory. Now here, you have a different vacuum depending on which viewpoint you're taking. Well, that could be fine. Stick to your vacuum and you're okay. That's okay unless you have, say, a big, baseball sitting on the table, and you're trying to put that into a superposition of being here and here. That's now making it a quantum object. Now you have to consider the gravitational field of the baseball. And now you're in trouble, because if you use the old, let's say the Newtonian view, which means putting a term in the Hamiltonian, that's fine. You've got no problem. But if you say that's not the right outlook, you should use the Einsteinian perspective, then you have this vacuum which is changing all the time, and you've got superpositions of different ones, then you're in trouble. How do you estimate the trouble? Well, you can make a measure of what's wrong, and say it's a kind of uncertainty in the system, and you take an integral of that over the whole system, and you see that uncertainty is an uncertainty in the energy of the system. And then you use the Heisenberg time-energy uncertainty relation,
Planck mass, I guess,
which says it gives you a lifetime. So that's a lifetime of the system, and that is a prediction. It says that if you have a system with a superposed baseball, it can only remain in that superposition for a certain length of time. For a baseball, it would be a ridiculously tiny fraction of a second.
Right.
So you have to have smaller things to get it bigger and bigger so that you could preserve this quantum state for long enough to see the collapse.
So you're saying that the linearity of quantum mechanics gets spoiled by gravitational influences. That's the perspective.
What I'm saying is, you want to be more even-handed. Lots of people talk about quantizing gravity,
Yeah.
and that's what you're supposed to do with the singularities. But you see, that's very far from what we could. You didn't have to look at physics at 10 to the minus 33 centimeters or something. That's hugely far from any measurement. But what about the other way around? Not the effect of quantum mechanics on gravity, but the effects of gravity on quantum mechanics. Now, that is much more within the scale of things we might be able to measure.
Right.
And there is an experiment which has been going on for, goodness knows, I don't know, a couple of decades by now, I think, by Dirk Barmester and colleagues of his, which he's getting pretty close to the stage of actually performing it. I think maybe within the next year or two, he might well see something. There are other experiments. I have a colleague, Yvette Fuentes, who has a plan for doing experiments with Bose-Einstein condensates, and there are other things people have in mind. I think that's a big, important area to try and do experiments to test, to see whether you can actually, without bringing in an observer or something like that, in a self-contained physical system, see a collapse of the wave function. Yeah.
Via gravitational influence.
Gravitational effect, yes.
Right. Is this why, for instance, you're not a fan of string theory's attempt to give a quantum theory of gravity, or is that a broader set of?
I think the trouble I have with that is more the dimensionality, the extra dimensionality. You see, I think that
Why does that bother you? You're this maverick thinker who has all these wild ideas. The possibility of more dimensions goes all the way back to Kaluza and Klein, in the early part of the 20th century.
Well, look, you see, I have my public and my private reason to object.
Okay.
And now I'm public. I have
slightly public, yeah. It's really just us and a few friends, really, listening in here.
Oh yeah, just a few friends. Well, the public reason was always to do with the arguments I've just been giving you. That there is a trouble with gravity. That I mean, you can't. The theories don't really coexist properly, and that no, I have a public reason, which is. That's one of the public reasons. The other one was more to do with the problems of the extra dimensions, as you were saying.
Yeah.
I mean, this tiny. I mean, you try to get rid of them by making them very, very small. But the trouble is when you're making them very small, you have problems with stability, the quantums. I mean, I did argue. I think don't want to go into this. I haven't really. Thought about these arguments for a long time. I haven't seen anybody contradict them. I have written a couple of papers on that. Why you would expect, and in books too, why we would expect these tiny little knots or whatever they are of extra dimensions tied up in little knots, why they would be unstable and they would decay and stuff like that. I think they would.
I mean, there are arguments. A lot of them invoke issues of supersymmetry, which again you can question, and then supersymmetry breaking and the effects of. But yeah, I mean, I certainly appreciate the concern. I guess my view is that there are issues worth thinking about, but by no means would it be enough to.
I think I never could. I think the trouble I had with string. Let me put it a different way.
Yeah.
The trouble I have with string theory is that it's really. Put it in a blunt way, it's being done by mathematicians. Now you see, I might be calling a mathematician. I hope I am. But I mean, this great strength of string theory and what's done is this amazing things it has done in mathematics. And I agree, it has done amazing things in mathematics. And we take Edward Witten and followers of him, and sure, there have been. They've made big inroads, revolutions in different areas of mathematics. That's completely true.
Yeah.
But when it comes to physics, I think you have to apply different criteria. And I think they're exciting theories to develop for that reason. And I have nothing against that at all. But to make them into physics is a huge stretch. Or a squash, I would put it not a stretch, it's the other way around. You've got to squash all these, and you don't see any evidence for the supersymmetry. You've got problems with that. You've got problems with the making the higher dimensions stable. I could never quite see, even with the with the supersymmetry, you have them stable, but still.
Right.
I really don't want to go into that too much.
It's okay. I guess I would just, and then I do want to move on to one final thing, if you'll grant us a few more minutes. I would say that for me, just from my perspective, the fact that you could extract general relativity from string theory, a quantum mechanical description of vibrating filaments, and you can pull Einstein's ideas out of it. If the history of science had gone in a different order, we would have had string theory before the general theory of relativity. And then with these extra dimensions, the ability, when appropriately thinking about them, to embrace all of the successes of the past: symmetry breaking, family structure of particles, discrete symmetries may be tied up with the geometrical form of the extra dimensions. It just strikes me that there's a lot of successes of the past that so naturally fit within string theory, which puts gravity and quantum mechanics together, at least on paper, in a consistent way. But I get your point. I mean, it is not yet connected to observable physics that we can test, and who knows when that will happen. So that's definitely
I think
worthy.
it's an aesthetic quality which is somewhat different. You see, I think there is an aesthetic which is important in mathematics, which is not quite the same as the aesthetic in physics. I think in a way it's been the mathematical one which has been driving the strings. Now, you see, I'm a great admirer of mathematical aesthetics and what you can do with it, and I think it's tremendous.
Yeah.
But I don't think it's spilled over into the physics. I think that the physics, it's a different thing. And I sort of think I really argue more with it on this point, because I think we could go on all night.
Yeah, no, I agree. But I can certainly see that. That's a valid point. But I wanted to turn to now a final topic, if you would, are some of the ideas you've been developing on consciousness, on what it is that's happening inside of our heads. You know, there's this deep, hard problem of consciousness. How is it that we have qualia, sensations of colors, emotions, thoughts, understandings? And my take on your position is that you are straight down the line physicalist. You are not imagining a dualist picture of the world. Is that correct?
Yeah. That's certainly the way I view myself. I mean, other people view me differently, but yes.
And so then the challenge is to understand what's happening up here in the language of physics, or the language of physics that we've yet to fully articulate. So one question along those lines is, many people use the metaphor of a computer as the model of thought processes inside the head. And you have come out with an argument that you feel that is a completely misguided metaphor, that what we do inside of our heads is not likened to the algorithmic approach, say, of a conventional computer.
I think we have to be a little careful, because there are different parts of our heads.
Yes, for sure. I think I mean understanding, the quality of human understanding.
I mean, if we talk about the cerebellum, I'm quite prepared to believe that may be a computer analogy might work very well.
Sure,
I mean,
sure.
As far as we know, it's completely unconscious, and of course, we don't understand how that works either. But the arguments, as you say, understanding. No, this goes back again to my graduate student days when I was in Cambridge. And I went to Cambridge to do pure mathematics, algebraic geometry. Even that I was doing a slightly offbeat kind of theory. But I decided I would like to go to other lectures on other topics. And I went to a wonderful course by Herman Bondi on general relativity, which was a great course. I went to a course by a mathematician called Steen, a logician, where I learned about computing machines. I learned about Turing machines. I knew what they were. I learned about Gödel's theorem. Now, I'd previously been worrying with a colleague of mine when I was an undergraduate, Ian Percival. We had lots of discussions about these things. And I was really troubled by the idea that Gödel's theorem seemed to prove that there were things in mathematics that were true and you couldn't prove. Okay, now I learn about Gödel's theorem in Steen's lecture. And the way I learn it, he made it very clear what it was, that you have a set of procedures of proof. Now, if you accept these procedures of proof, and that if they come up with, feed in the theorem, chug, 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 if it comes up and says, yes, it's true, then by examining the methods of proof in the procedures, you look at the axioms and the well, you divide it up into maxims and method. Well, never mind all that stuff. As long as you believe, you look at the first one and say, okay, yeah, that's okay. Anything you get from that must be tracked. That's true. That's all right. That's all right. Not sure about that. Ah, it's okay. I see why that works. You go through all that. Anything that, if it comes up with yes, it's true, then you believe it's true. Gödel produces a statement which your belief in its truth is actually outside your understanding that it's true. I mean, it's amazing. I just thought that's absolutely stunning. You show this thing is true, but cannot be proved by means of those proof methods. You prove it by means of your belief in the trustability of those truths, by your trust, your understanding of those proof procedures. That goes beyond the following of the truth procedures. Now, what does it mean by understanding it? Well, it's something about your conscious goings on. And I had the view that it's got to be something non-computational. And it's not a Turing machine. Of course, it might be a Turing machine which is so complicated that we could never understand it. But then the argument, went through all complicated things, mainly in my book, Shadows of the Mind, which followed the Emperors of Mind. But really, the argument is much simpler than that. You say, well, it's nice to pick on a theorem which I didn't know at the time, which is a theorem called Goodstein's theorem. It's a really lovely theorem. It's proved in 1945, where you take any integer and you write it in the binary form, which means sums of distinct powers of 2. And then you look at the exponents and you say those are numbers which are not written that way. So you write those as distinct powers of 2. And then you look at the indexes and you go on, and this chain comes to a limit. And then you have two procedures. You look at that number and you replace all the, replace all the 2's by 3's. The number's got hugely larger. Then you subtract 1. Replace all the 3's by 4's, subtract 1. 4's by 5's, subtract 1. Goodstein's theorem says that this procedure always ends with 0. Now, someone give lectures with that, and you say, okay, try it with 3. It comes down. Try it with 4. I would not recommend using your laptop, programming it into that. I would not recommend using your mainframe. I would not recommend using any computer known on the planet. Take out a piece of pad of paper and a pencil and work it out yourself. You can see why it comes. It's tricky. If it was 4, you can see why it comes down. It's a little trickier to see why for any number it comes down. It depends on something called transfinite induction. Okay. But the point about this is not that. The point about this is, how do we know it's true? How did evolution produce in this algorithm in our heads by natural selection something which is so complicated from the experiences of our ancestors, killing saber-toothed tigers or whatever they were doing, domesticating animals, growing crops. That's nothing to do with this kind of stuff. Right. What we've developed is this general concept, procedure, whatever it is, of conscious understanding. So my argument was that it cannot be the production of some very complicated algorithm, because natural selection could never have come across something that we can see it's true by simple reasoning. I mean, try it before. I don't have to go to the transfinite thing. You can try it before. So, okay. So then I thought, I didn't know about Goodstein at that time, but I knew about the Gödel theorem. Then I thought to myself, well, there's something going in our heads which must be non-computable. What kind of physics can it be? Well, there's the continuum problem, and you put things on a computer. Well, I didn't think that was probably it. You can get good approximations. That's a point which you have to worry about it. But I didn't settle on that. I just thought that's not the problem. Well, what about Newtonian dynamics? Well, you could put that on the computer. What about general relativity? Yeah, I could put that in. Well, now we even know, because with these wonderful calculations and LIGO and all that stuff, sure, you can put that on a computer. Hard to do, but still. Computational calculations. What about quantum mechanics? Then I thought about Dirac's first lecture. What did he do? He took out a piece of chalk. He was talking about, first of all, about particles. And he said, well, an electron could be here, and it could be here. And in quantum mechanics, it can be here and in here at the same time. You can have a superposition of this state and that state, and that's a quantum state can involve superpositions. What about a piece of chalk? And he took out a piece of chalk, put it here and here, and I think he then broke it in two. Now, the trouble is, when I say I think, my mind wandered, and I think I was looking out of the window and thinking about something else. I have no idea what. When my concentration came back to the lecture, he'd gone on to the next thing. I vaguely remembered him mentioning something about energy, but I had no idea what it was that resolved this problem. So I was left with this puzzle of the collapse of the wave function. And so I thought, well, that must be it. That must be where there is something non-computational going in. So I eventually, well, I thought I eventually would write a book about it. And I had this idea that I would write that became The Emperor's New Mind. Around about the same time, Stephen Hawking was writing his brief history of time. I remember, yes, he got, who did he got to write the forward? See that time, not many people knew about him, and I kept wondering, you know, is this great physicist, a great thinker, and nobody seems to have known about it. I remember wheeling around in his wheelchair and thinking that.
Yeah.
And at that time, he wasn't very well known. But then after the brief history, yes, it was. You just told him his name, yes. What's his name? The one who wrote the foreword. Never mind.
I'm not sure actually.
No.
Yep.
He was a well-known expositor of science in the US.
You're saying he wrote the foreword to Hawking's A Brief History of Time?
That's right, yes. So I thought, well, I've got to think.
I don't even know who that was at the time. And someone in the chat will no doubt tell us.
There was. He wrote.
Yeah.
So I thought, well, I need somebody to write it. So I thought of Martin Gardner.
Yeah.
So I sent my book to Martin Gardner. I'm not sure I'd finished it at that point. I read it to him, and I would not be nervous about what he thought. He said, "No, I agree with you."
Right.
And he was very happy to write her. So I thought then, okay, well, at least the book probably won't disappear without trace.
Right.
But it probably
did more than that. Absolutely did more than that, of course. But if you're hanging your hat on incomputability being in the measurement problem, does it disturb you that there are proposed solutions to the measurement problem that are computable, like we were talking about before? You know, the Bohm, de Broglie.
I don't think that's correct. You see, that's all. Yeah.
You just think they're wrong. Okay.
Yeah. No, I think they were wrong.
Right.
Well, that's right. It's a great challenge. How do you make a measurable? How do you make a
theory that's in
theory which is non-computable? You see, there are.
Are there?
Here's old Dirac again. You see, this is interesting. I don't know whether this is. It's a nice example, and I think it could be a representative. Dirac didn't just discover the equation of the electron, but he had a period of his life where he studied classical electrodynamics. Now, why on earth was he doing that? I don't really know, but he was looking at classical particles and how do they, and he ran into this equation because he was looking at the self-acceleration problems. You have to look at
sure.
And then he got to these self-accelerating particles or exponential behavior. And so you have to you now have a third order equation. It's got too many parameters because you've got all these runaway solutions.
Yes.
But how do you get rid of the runaway solutions? Well, you've got to look to see eventually, is it going to run away? It's like a Turing machine. You've got to know, is that Turing machine ever going to stop or not? I think it's probably a non-computable problem.
You think it's non-computable to determine whether you'll have a runaway? I see. You're saying that it may be a long time in the future that the electron just takes off or something of that sort.
I mean, I don't know. I don't have a proof of that. But at least it's a candidate.
Right.
Because it's looking to the ultimate future. You're saying, is this solution is to be regarded? This solution is to be discarded
if at any point it runs away.
It runs away, and the runaway is that it goes on computing and the space goes out to infinity, so it doesn't work.
Gotcha.
Something like that. I mean, I don't know whether it's not computable, but I think it's an interesting candidate.
So one final question that's related to this. Do you think that Gödel's incompleteness theorem tells us something specific about the ultimate physical laws?
Yeah.
What do you think it tells us?
Well, I do. I wouldn't have said that necessarily. You say only because it contain the physical world contains conscious beings. You see,
Okay,
and so I argue that conscious beings.
fair enough.
When I wrote the book, I tried to learn up about neurophysiology, and I did learn. I learned about the Hodgkin-Huxley nerve propagation and all that stuff. And then I thought, what? That's not going to have a hope. You see, how can you preserve quantum coherence in nerve propagation when you've got these electric fields propagating right into the brain?
Right.
It seemed to be hopeless. And so at the end of the book, I just did a fuddled argument, which I didn't really believe. And that was it. A bit of a denouement, I didn't know. But then
You hooked the hammer off, I guess, right?
Namaroff read my book, and he wrote to me. I get lots of letters from people who, for a little bit, crazy theorists from time to time. And I thought, here's another one, you see. And he talks about these microtubules. What are they, you see? But then he's got pictures of them. So, well, they must be real. So I look them up and I thought, gosh, they are real. Now, they're much more promising, not just because they're smaller, they're tubes. And well, I didn't even know the difference between A and B lattices, but the A lattice microtubules are extremely symmetrical. And I think I was aware of the fact there's a thing called the Jahn-Teller effect, that if you have symmetrical molecules and things like that, then you can have a ground level in the quantum system which is shielded, which is degenerate. So you can have information in the ground level, which is shielded from excited level. So there's a much better chance in these little tiny tubes, which are, well, they're in pretty well all cells, not quite all cells, but in most cells, but most of them are B lattice where the symmetry is not so big. So you've got to look for highly symmetrical cells. I don't mean cells, highly symmetrical structures within the cells,
Sure.
which might preserve some kind of quantum coherence. Well, it's very speculative. I'm not saying it's anything less than speculative, but all these discussions of consciousness.
But even if you were right, or it's a stepping stone to be right, do you agree that this approach would still leave open the mystery of why we have inner sensations at all? I mean, that hard problem of consciousness is still, it seems to stand beyond any of the ideas we're talking about. Do you agree with that?
I think things are mysteries when you don't, you see, people used to worry about lodestones, didn't they? And these mysterious fields that there were, some mystical fields.
Right.
And they're still mysterious, you don't see them. But you understand them because you've got a beautiful theory of them. And you can make them do things for you, like radio waves, and you can, you've got Maxwell's equations that do it. And then you've got quantum electrodynamics, which make you do things which, transistors and goodness knows what, which, sure. And does it remove the mystery just because you have a theory which describes them? I don't think it does.
Some would say that's an unfair analogy to draw, though, because all of those examples are third-party available phenomenon, objective qualities of the world. And when we get to conscious experience, it's the one thing that's only available subjectively. So it stands outside all those analogies.
I don't think it is only available subjectively. And here we go back to Stuart Hameroff. I mean, what does he do? What's his day job or night job? I'm not sure whether it's day or night. He puts people to sleep, well, in quotes, because he says it's different from sleep. He puts people under general anesthetics. And he's extremely interested in what this is actually doing. What kind of substances do it? It's not a chemical effect because the different materials which put you to sleep are not chemically related.
Right.
It's some physical process or something. Okay, I mean, it means you can probe consciousness.
Well, you see, not just you can't probe it. So, I mean, even, psychedelics, right? One can probe it in many, many different ways. But
that's true.
I can't get inside your head and you can't get inside my head.
What do you mean by getting inside it? You see, I don't know. I mean, sure, you don't have wires attached to one person's head, and so you can know what somebody else is thinking. You might have someday.
Right. Yeah, at that point, maybe one would think of it as an objective quality, and the analogy might.
I can see the trouble you have of thinking of things as internal in some sense.
Right.
But I'm not trying to make theories about it.
Sure.
So, I mean, I can see why people think it's some you could see it's an excuse for not worrying about the problem. And I think
Right.
that's
I
probably
agree.
true in quantum mechanics. If you look back at what the old people, when they were young in those days, used to think about quantum mechanics.
Pioneers, we'll call them the pioneers.
Pioneers, absolutely. And a lot of them thought that it was the conscious perception
Yeah.
which reduces the quantum state.
Yeah. Wigner. Yeah.
Yeah, I know. I talked to Wigner about these things.
Yeah.
Von Neumann.
Did you think that it was nutty when you heard about when he would say things like that?
No, I didn't think it was nutty.
Mm-hmm.
I didn't. No, he was fairly broad-minded about these things. He thought this was one point of view.
Mm.
So I think I never thought. I don't think. I like all these things. I think you've got to have a stage in your life where you believe some of these things.
Right.
So there was a stage in my life where I thought, I thought many worlds made sense, things like that.
Yeah, I went through that period too.
Yes. Well, I had a stage in my life where I thought string theory was a wonderful idea. Actually,
I'm still in that idea.
Yeah. No, I still do. It's just I like the strings. I never have anything against the strings. It's just
good. I'm glad to hear that.
When the dimensions went up too high, that's what worried me.
Right.
But,
so I mentioned that was a final question, but if you don't mind, I do have one final point that I'd like to just end on. There's been a lot of interesting work lately on the information paradox in black holes.
Oh God,
where everything is heading toward, I think, a communal belief, at least among the string theorists and many quantum gravity people, that information is not lost in black hole evaporation. Stuff falls in, it evaporates, and you could, in principle, recover the information that fell in. You're not of that perspective, right?
Absolutely not. Yes. Yeah.
And can you tell us why?
There's a question about how much of it is in the radiation. Yes. I mean, I guess I used to think most of it was destroyed in the singularity, but I think Don Page was arguing that it's about 50-50.
50-50, right.
It doesn't make much matter. When it comes to the Hawking points, it all goes squizzle through those points anyway, so it doesn't make much difference. No, but there has to be a non-unitary behavior there in the... No, look, 50-50 is pretty bad, isn't it?
But now the Page curve, there are arguments, right, that are inspired by string theory, but right within the structure of gravity, general relativity, that you can understand the Page curve, you can understand the entanglement. It all seems to be holding together in a way that's unitary.
Yes, but look, here you've got a singular. Think of the conformal diagram. You've got a singularity here. You've got points out here. You've got information which you've got particles which get destroyed on the singularity. You've got its partner, say an EPR partner, which goes out the other side.
Right.
Now, one of the dictums of quantum mechanics is you can't copy information.
Sure. No cloning theorem.
If you're saying no cloning theorem, now if you're saying this information is retrieved in the exterior, well, it's copying what's gone into the singularity.
Yeah, I mean, the arguments that some are putting forward, Susskind, Maldacena, others, that in some sense the outside and the inside really should be thought of as distinct, and they're really describing in some sense the same state as opposed to a copy of a state. But maybe that will take us too far afield to plumb the depths of those arguments.
You won't know what I think, and you're quite right. I don't believe it.
Right. That's certainly the point I wanted to get to. Which,
actually, in some sense, I've slightly shifted my view on that. So maybe it's worth asking me, because my view usually was, okay, quantum gravity, whatever it is, you're applying quantum gravity theory. It's not the right theory. It's got to involve the collapse of the wave function.
Mm-hmm.
So any argument which, and I still believe this argument, any argument which depends on unitarity at this level, where you've got a hugely
too early, it's missing a part of the story.
You're missing on a monstrous part of the story,
No.
Not just the tiddly part. Maybe most gravity phenomena you see are missing a little tiny part, but no, this is the main picture.
No, totally understand.
So that you've got to find a very gravitized quantum mechanics. You can't use arguments from unitarity. That's just no. That would be my normal argument against it.
Sure.
It's still my argument. I mean, certainly you don't want any firewall or anything. I don't know what's the current view on firewalls.
Well, that's an interesting question. So I think the current view on firewalls is that from a certain perspective, it would be as if there's a firewall. Because in some sense, the gathering up of the external information changes the system in such a way that generates the firewall. So it's not abstractly that it's there, but it's the act of acquiring the information that causes the firewall to exist. At least I asked this very question last week to Juan Maldacena, who gave a colloquium at Columbia on the latest thing. And that was the answer, at least that I understood, that he gave. I've not investigated it fully enough on my own.
And drove you took a spaceship towards the galactic center.
Yeah. Would you encounter a firewall? I don't know how these new ideas impact the.
You don't see it, do you? In
Sure.
the Event Horizon Telescope, there's no.
Yeah. Right. Exactly. So these things are not just abstract anymore.
No,
So anyway, it's been a great conversation, Roger Penrose. Thank you so much for spending the time. We covered quite a lot of ground, you know, from the early aha moments through ideas of black holes in the 60s, through cosmological ideas, through quantum mechanics, measurement, consciousness. We've sort of covered it all, which is great. So thank you so much.
You got away without mentioning twisted theory.
Yeah, we haven't done twisted theory. Yeah, so that'll be our next conversation. So we'll announce that at some point. Enjoy the ceremony next week, which is well-deserved honor, winning the 2020 Nobel Prize in Physics, and much success with all these wonderful ideas going forward. I'm just excited to see where it all lands out. So again, thank you for joining us, and congratulations again.
Thank you very much indeed.
Thank you. All right, everyone. So we've been at it for 2.5 hours now. I think, unfortunately, I'm not going to do much more because I desperately need to use the facilities. I can't sit this long as I used to, but I hope you enjoyed the conversation with Roger Penrose. A lot of wild ideas, really, and the amazing thing is that it's not just ideas in a vacuum. These are ideas now that have at least some of them been tested through the observation of black holes. So in any event, we will continue to have these sessions on a semi-regular basis. As I mentioned before, happy to hear your suggestions. Many of you do suggest that we have a conversation with Roger Penrose, which I'm glad that we have done. And I'm looking forward to our getting together sometime soon. Again, sign up for the World Science Festival newsletter. Follow World Science Festival on YouTube. If you want to follow me on Twitter, I always announce these events there too that we're having. I'm at @bgreen on Twitter. I don't even know what my handle is on Facebook. I don't use it that much anymore. I probably should. And my son tells me I should start using Instagram. So for those of you in the younger side of things, Instagram, at some point soon, I will start using that as well. Again, thanks for joining us. Looking forward to our next session. Look out for the announcement of when that will be. Okay, Brian Greene signing off.